At this precise moment, roughly 400 million miles from where you sit, a machine the size of a basketball court is hurtling through the void at 17,000 miles per hour. Its solar panels span over 100 feet from tip to tip, the largest ever flown to the outer solar system, and they are pointed toward a sun that appears as little more than an unusually bright star. The spacecraft carries 9 scientific instruments, 16 engines, enough propellant for 54 planned maneuvers, and a single, devastating question that humanity has asked for 3,000 years, but has never before committed the resources to answer. Are we alone in the universe? The Europa Clipper launched from Kennedy Space Center on October 14, 2024, atop a SpaceX Falcon Heavy rocket, and it will not arrive at its destination until 2030. 6 years of silent coasting through interplanetary space, a gravity assist from Mars, another from Earth, and then the long spiral into the Jovian system where the most tantalizing world in our solar system waits beneath a shell of ice. Europa. A moon slightly smaller than our own, unremarkable in appearance, a cue ball of cracked ice drifting in the radiation-soaked shadow of the largest planet in our cosmic neighbourhood. And yet, beneath that frozen surface lies an ocean, not a lake, not a reservoir. An ocean containing twice the volume of all the water on Earth, kept liquid by forces that have nothing to do with sunlight, heated from within by the relentless gravitational kneading of Jupiter's tidal grip. An ocean that has existed dark and deep and possibly churning with chemistry for billions of years. An ocean that may, at this very moment, harbour life. We are sending a spacecraft to find out. The question has been committed to hardware, to trajectory, to the inexorable mathematics of orbital mechanics. The Europa Clipper cannot be recalled. It cannot be redirected. It will arrive at Jupiter in 2030, and it will begin a systematic investigation of Europa's ice shell, its hidden ocean, and its potential for biology. Within a decade, we will have data. Within a decade, we may have an answer. And here is what should unsettle you, what should make you pause before you celebrate this achievement of human curiosity and engineering. We may not be ready for what we find. If you find yourself captivated by the profound questions that lie at the edge of human knowledge, consider subscribing to this channel and leaving a like. Your support genuinely helps bring these stories to the audience they deserve. Are you ready to understand what we have set in motion? Let us begin with the moon itself. Europa was discovered on January 8, 1610, by Galileo Galilei, using a telescope of his own construction with a magnification of roughly 20 times. He observed it alongside Io, Ganymede, and Callisto, the 4 largest moons of Jupiter, which would later bear his name as the Galilean satellites. Galileo recognized immediately that these points of light orbiting Jupiter were moons, worlds in their own right, and that their existence shattered the Aristotelian cosmology that had placed Earth at the center of all celestial motion. If Jupiter could have moons, then Earth was not unique. If other worlds could be centers of orbital motion, then perhaps other worlds could be centers of other things as well. For nearly 4 centuries after Galileo's discovery, Europa remained a point of light. Astronomers measured its orbit, calculated its mass, estimated its density, and noted that its surface appeared unusually smooth compared to the crater-pocked faces of other moons. But they could not see what lay beneath. They could not know what they were looking at. The transformation began in 1979, when the Voyager 1 and Voyager 2 spacecraft swept through the Jovian system on their grand tour of the outer planets. The images they returned were revelations. Europa's surface was indeed smooth, but not in the way of a pristine, untouched world. It was smooth in the way of a frozen lake that has cracked and refrozen, over and over again across geological time. The moon was covered in a chaotic network of reddish-brown lines, some stretching for thousands of miles, crossing and intersecting in patterns that suggested a surface in constant motion. There were almost no impact craters, which meant the ice was young, constantly renewed, erasing the scars of asteroid bombardment that pockmark every other solid body in the solar system. The Voyager scientists stared at these images and began to formulate a hypothesis that would take decades to confirm. If Europa's surface was young, something must be resurfacing it. If the ice was cracked in these particular patterns, something must be stressing it from below. And if the stress came from below, there must be something below that was capable of movement. Water, liquid water, an ocean. The Galileo spacecraft, which entered orbit around Jupiter in 1995, spent 8 years investigating the Jovian system and transformed the Europa hypothesis into something approaching certainty. Galileo carried a magnetometer, an instrument designed to measure the magnetic field around Europa as the spacecraft flew past. What it detected was astonishing. Europa had an induced magnetic field, a field that could only exist if the Moon contained a global layer of electrically conductive material beneath its surface. Ice is an insulator. Rock is a poor conductor, but salt water, water rich in dissolved minerals, conducts electricity beautifully. The measurements were unambiguous. Europa's induced field varied precisely as you would expect if it were generated by a global ocean of salt water responding to Jupiter's rotating magnetic field. The ocean was real. It was there, right now, hidden beneath somewhere between 10 and 20 miles of ice, containing an estimated 3 billion cubic kilometres of liquid water. For comparison, all the oceans on Earth combined hold approximately 1.335 billion cubic kilometres. Europa's ocean, on a moon less than a quarter the diameter of our planet, holds more than twice as much water as our entire world. But water alone does not make a world habitable. The Mariana Trench contains water. The cores of gas giant planets contain water. Water is common in the universe, abundant beyond easy comprehension, found in comets and asteroids, and the atmospheres of distant worlds. What makes Europa extraordinary is not simply that it has water. What makes Europa the most compelling target in our search for life beyond Earth is how that water stays liquid, what energy sources might exist within it, and what chemistry might be happening at the boundaries where ice meets ocean and ocean meets rock. Europa orbits Jupiter once every 355 Earth days, and its orbit is slightly elliptical, not because of any initial condition, but because of gravitational interactions with its neighbouring moons Io and Ganymede. This ellipticity is crucial. As Europa swings closer to Jupiter, and then farther away over the course of each orbit, the gravitational pull on the Moon varies. Jupiter's gravity distorts Europa, stretching it slightly when it is closer, allowing it to relax slightly when it's farther. This continuous flexing, this endless gravitational kneading, generates heat through friction within Europa's interior. The process is called tidal heating, and it is the same mechanism that makes Io the most volcanically active body in the solar system. On Io, tidal heating is so intense that the Moon's surface is constantly renewed by erupting lava, and the temperature at volcanic vents exceeds 1800 degrees Celsius. Europa experiences less intense tidal heating than Io, because it orbits farther from Jupiter, and its orbital eccentricity is smaller, but the heating is sufficient. It is more than sufficient. It keeps an ocean liquid in a region of space where sunlight provides less than 4% of the warmth it provides at Earth, where the equilibrium temperature is approximately minus 260 degrees Fahrenheit, where any body without internal heat would be frozen solid to its core. The ice shell insulates the ocean from the killing cold of space. The tidal flexing pumps energy into the system, and at the bottom of that ocean, where water meets the rocky mantle of Europa's interior, there may be hydrothermal vents. On Earth, hydrothermal vents are fissures in the ocean floor where seawater percolates down through cracks in the crust, becomes superheated by magma, and erupts back into the ocean carrying a cargo of dissolved minerals. These vents create underwater chimneys called black smokers that spew plumes of mineral-rich water at temperatures exceeding 700 degrees Fahrenheit. The water should be sterile. The pressure should be crushing. The darkness should be absolute. And yet, when scientists first explored Earth's hydrothermal vents in the 1970s, they discovered ecosystems of staggering abundance and complexity, thriving in conditions that should be lethal to all known life. Giant tube worms up to 6 feet long, with no mouths and no digestive systems, deriving all their energy from symbiotic bacteria that metabolize hydrogen sulfide. Ghostly white crabs and shrimp clustering around the vents in densities of hundreds per square metre. Mats of bacteria so thick they coat the rocks in white and yellow slime. Fish, octopuses, mussels, clams. Entire food webs based not on photosynthesis but on chemosynthesis, drawing energy not from sunlight but from the chemical gradients between vent fluid and seawater. The discovery of hydrothermal vent ecosystems revolutionized our understanding of where life could exist. Before 1977, the assumption was that all life on Earth ultimately depended on the sun. Plants captured sunlight, herbivores ate plants, carnivores ate herbivores, and decomposers recycled the remains. Remove the sun, and the entire system would collapse. But the vent communities proved that an alternative existed. Life could be powered by the Earth itself, by the heat and chemistry of a planet's interior, by energy sources that had nothing to do with the nearest star. If life could evolve at hydrothermal vents on Earth, it could evolve at hydrothermal vents on Europa. The Moon has the water, it has the heat source, it almost certainly has the rock-water interface where chemical gradients could form. And it has had all of these things for billions of years, potentially since before life arose on Earth, continuously, without interruption, in an environment shielded from the radiation bombardment that sterilizes Europa's surface. The surface of Europa is among the most hostile environments in the solar system for any Earth-like life. Jupiter's immense magnetic field traps charged particles from the solar wind and accelerates them to tremendous energies, creating radiation belts that would deliver a lethal dose to an unshielded human in approximately 10 minutes. The surface ice is constantly bombarded by this radiation, breaking apart water molecules and creating a thin atmosphere of hydrogen and oxygen, while also producing reactive chemicals like hydrogen peroxide that permeate the upper ice layers. Nothing could survive on Europa's surface for long, but 10 miles down, beneath the radiation-absorbing ice, the ocean is shielded. The radiation cannot penetrate, the temperature is stable, the chemistry may be rich, and if hydrothermal vents exist, pumping energy and nutrients into the deep water, then Europa's ocean could be habitable, not merely survivable, but actively conducive to the chemistry that leads to life. This is the hypothesis that has driven planetary scientists for decades. This is the possibility that convinced NASA to commit over $5 billion to building and launching the Europa Clipper. This is the question we have sent a spacecraft to answer. Is Europa's ocean habitable? And if it is habitable, does it harbour life? The Europa Clipper will not land on Europa. It will not drill through the ice. It will not directly sample the ocean. The spacecraft is an orbiter, designed to conduct a systematic investigation of Europa from a safe distance, making 49 close flybys of the Moon over the course of its primary mission, while spending most of its time farther from Jupiter where radiation levels are lower and the spacecraft's electronics can survive. Each flyby will bring the Clipper within 16 miles of Europa's surface, close enough to image features as small as a football field, close enough to probe the ice with radar that can penetrate kilometres into the shell, close enough to analyse any material that Europa might be venting into space. And this last capability may be the key to everything. In 2012, the Hubble Space Telescope detected what appeared to be plumes of water vapour erupting from Europa's south polar region. The observations were tentative, at the very limit of Hubble's capabilities, and subsequent observations have yielded inconsistent results. Sometimes the plumes seem to be there, sometimes they do not. The reality of Europa's plumes remains uncertain, but if they exist, they change everything. A plume would mean that material from Europa's subsurface, possibly from the ocean itself, is being ejected into space where a spacecraft could fly through it and capture samples directly. No landing required, no drilling required, just a well-placed flyby through a fountain of oceanic material, and the instruments on board could analyse that material for organic molecules, for chemical signatures of biological activity, for the fingerprints of life. The Europa Clipper carries an instrument called the Surface Dust Analyzer, designed to capture and analyse particles that the spacecraft encounters during its flybys. It carries a mass spectrometer called MassSpecs that can identify the molecular composition of any gas it samples. If Europa is venting material into space, the Clipper will find it, sample it, and tell us what it contains. Even if no plumes exist, the Clipper's other instruments will map Europa's surface in unprecedented detail, revealing the processes that create its young, fractured terrain. The ice-penetrating radar will probe the structure of the ice shell, potentially detecting the ocean boundary beneath. Thermal instruments will identify hotspots where fresh material may be welling up from below. Gravity measurements will constrain the thickness of the ice and the depth of the ocean. By the time the primary mission ends, we will understand Europa better than we understand many places on our own planet. But understanding Europa is not the same as finding life. The Clipper will tell us whether the conditions for life exist, It will tell us whether the chemistry is right. It may even find organic molecules, complex carbon-based compounds that are the building blocks of biology as we know it. What it cannot do, by design, is definitively confirm or deny the presence of living organisms. That will require a future mission, a lander or perhaps a submarine, capable of directly sampling the ocean. The Clipper is the reconnaissance mission, the scout sent ahead to determine where we should look more closely. And yet, even a reconnaissance mission can make discoveries that transform our understanding of the universe. The detection of organic molecules in Europa's plumes would be a finding of historic magnitude. The identification of chemical disequilibria that can only be explained by biological processes would be a paradigm shift. The mere confirmation that Europa's ocean is habitable, that conditions exist where life as we know it could survive, would mark the end of an era in which humanity wondered whether such places existed elsewhere, and the beginning of an era in which we know they do. The Europa Clipper represents an irreversible commitment. The spacecraft is en route. It will arrive. It will conduct its investigation, and the results will filter back to Earth at the speed of light, taking approximately 40 minutes to cross the gulf between Jupiter and our world, carrying data that we cannot undiscover, knowledge that we cannot unknow. For the entirety of human history, the question of extraterrestrial life has been philosophical. We have wondered, speculated, argued, and imagined. Aristotle thought the heavens were perfect and unchanging, unsuitable for the messy business of biology. Giordano Bruno believed that an infinite universe must contain infinite worlds, many of them inhabited, and was burned at the stake in 1600 for his cosmological heresies. Modern scientists have calculated the probability of life arising, debated the Fermi paradox, listened for radio signals from intelligent civilizations, and searched for biosignatures in the atmospheres of exoplanets light years away. But through all of this, the question has remained abstract. We have had opinions, not data, hypotheses, not answers. The Europa Clipper changes the nature of the inquiry. For the first time, we are sending a spacecraft to a place where life might actually exist, with instruments designed to detect signs of that life, following a mission plan that will systematically investigate the evidence. We are no longer wondering, we are looking. We are actively, deliberately, irrevocably seeking an answer. The journey from speculation to investigation has taken nearly half a century. The first serious scientific proposal to explore Europa came in the early 1970s, when the potential for a subsurface ocean was only dimly understood. The Voyager flybys galvanized interest, and the Galileo mission confirmed the ocean's existence, but every subsequent proposal to return to Europa was defeated by budget constraints, technical challenges, or shifting priorities. NASA studied a Europa orbiter in the late 1990s, then shelved it. They studied a Jupiter Icy Moons orbiter in the 2000s, then cancelled it. The European Space Agency planned a mission called Laplace, which evolved into JUICE, the Jupiter Icy Moons Explorer, but that mission prioritizes Ganymede over Europa. The persistence of the scientific community eventually prevailed. In 2013, Congress directed NASA to begin work on a dedicated Europa mission. The mission concept evolved through multiple iterations, from a flyby to an orbiter to the current architecture of a Jupiter orbiter that makes repeated Europa flybys. The Europa Clipper, as it came to be called, survived budget reviews, design changes, launch vehicle debates, and a pandemic that disrupted assembly and testing. On October 14, 2024, it finally launched. The mission cost approximately $5 billion. The spacecraft took 12 years to design and build. The scientific team involves hundreds of researchers across dozens of institutions. The stakes could not be higher. If the Clipper finds evidence suggesting life, it will be the most significant discovery in the history of science, the confirmation that biology is not a cosmic accident unique to Earth, but a phenomenon that arises wherever conditions permit. If it finds a habitable but apparently lifeless ocean, it will constrain our understanding of life's origins and force us to confront the possibility that life is rare, that we are alone, that the universe is vast and ancient and fundamentally empty of minds to appreciate its wonders. Either answer changes everything, either answer demands a response, and we have committed through the act of launching this spacecraft to receiving one of these answers within the next decade. The trajectory that carries the Europa Clipper to Jupiter is not a simple straight line. The spacecraft does not have enough fuel to fly directly from Earth to Jupiter and slow down into orbit around the giant planet. Instead, it follows a path that uses gravity assist to gain the velocity it needs. On March 1st, 2025, the Clipper flew by Mars, using the planet's gravity to bend its trajectory and add to its speed. On December 2nd, 2026, it will return to Earth, swinging past our planet in a maneuver that will give it the final velocity boost needed to reach Jupiter. The Earth flyby will be precise, calculated to within a few kilometers, threading the spacecraft through a gravitational needle that will sling it outward toward the outer solar system at over 50,000 miles per hour. Between maneuvers, the spacecraft coasts, its systems largely dormant, its solar panels drinking the slowly dimming sunlight, its trajectory curving imperceptibly toward its distant target. The journey is silent and patient, measured in years and hundreds of millions of miles, a testament to the precision of orbital mechanics and the patience of the engineers and scientists who designed it. When the Clipper finally arrives at Jupiter in April 2030, it will face the most challenging radiation environment ever encountered by a spacecraft in long-term operations. Jupiter's radiation belts make the Van Allen belts around Earth look gentle by comparison. The charged particles are more energetic, more numerous, and more penetrating. They would destroy unshielded electronics within days, corrupting memory, triggering phantom commands, gradually degrading systems until failure becomes inevitable. The Clipper's designers confronted this challenge with a two-part strategy. First, they minimized the time the spacecraft spends in the worst radiation zones by designing an orbit that takes it far from Jupiter most of the time, bringing it close to Europa only for brief flybys before retreating to safer distances. Second, they encased the spacecraft's most sensitive electronics in a titanium vault with walls nearly half an inch thick, shielding the computers and control systems from the worst of the radiation. The vault weighs almost 500 pounds, a massive penalty in a domain where every gram costs fuel, but it is essential for survival. Even with these protections, the Clipper's lifetime in the Jovian system is limited. The spacecraft is designed to complete its 49 Europa flybys over approximately 3.5 years. After that, accumulated radiation damage will begin to degrade its systems, and the mission will end. If NASA can extend the mission, they will. But the Clipper is fundamentally a mortal machine, built to answer specific questions within a specific time frame, and then to fall silent. The silence, when it comes, will not diminish what the Clipper has learned. The data will be on Earth, in the archives, available for analysis for generations. The images will become part of our collective vision of the solar system, as iconic as the Voyager images of Jupiter's Great Red Spot, or the Cassini images of Saturn's rings. And the answer to the question, whatever that answer turns out to be, will be ours forever. The question humanity has asked since we first looked up at the night sky and wondered whether the lights we saw were other suns, other worlds, other homes. The question that has motivated 1 billion science fiction stories and 1,000 scientific careers. The question that the Europa Clipper was built to address. Is there life elsewhere in the universe? We will not know by tomorrow. We will not know next year. The answer will come in pieces, in data packets, in spectra, and images, and measurements that must be analysed and debated and verified. The answer, if it comes at all, will be cautious and hedged and loaded with caveats. Scientists do not announce discoveries of cosmic significance lightly. They test and retest. They invite criticism. They demand replication. The process is slow, deliberately so, designed to prevent false positives from misleading the world. But the process has started. The spacecraft is en route. The question has been committed to hardware, to trajectory, to the mathematics of interplanetary navigation. The Europa Clipper cannot be recalled. To understand what the Clipper might find and why finding it would matter, we must first understand what we know and do not know about life's origins. How did life begin on Earth? Could that same process occur elsewhere? And what would it mean if it did? The oldest known evidence of life on Earth dates to approximately 3.5 billion years ago, and possibly earlier. The evidence takes the form of fossil stromatolites, layered structures built by ancient microbial mats in shallow seas, and microscopic carbon isotope ratios in ancient rocks that suggest biological processing of carbon. Life appears to have arisen quickly, geologically speaking, within the first few 100 million years after the planet's surface became cool enough to support liquid water. This speed suggests one of two things. Either life arises easily and quickly wherever conditions permit, or Earth was extraordinarily lucky in its early history. We do not know which interpretation is correct. We have exactly one example of life arising, one data point, and from one data point we cannot determine probabilities. If life arose quickly on Earth because the chemistry is inevitable, then life should be common throughout the universe. If life arose quickly on Earth because of a chain of wildly improbable accidents, then we might be alone, the sole winners of a cosmic lottery with infinitesimal odds. Europa offers a chance to add a second data point. If the Clipper finds evidence that life exists, or once existed, in Europa's ocean, the implications would be staggering. It would mean that life arose independently at least twice in a single solar system, suggesting that the chemistry leading to biology is not a fluke, but a predictable outcome of planetary processes. It would mean that the universe is likely teeming with life, that microbial ecosystems probably exist wherever liquid water persists for long enough, that the question is not whether life exists elsewhere, but how common it is, and how far it has evolved. If the Clipper finds a habitable but lifeless ocean, the implications would be equally profound but far more troubling. It would suggest that something about Earth's early history was special, that the chain of events leading from chemistry to biology is not easily replicated, that life is rare and precious, and we are perhaps among the only minds in a vast and empty cosmos. Either answer changes our understanding of our place in the universe. Either answer demands a rethinking of philosophy, theology, and our responsibilities to other life forms. Either answer is worth knowing, even if the knowing brings discomfort. The Europa Clipper was not designed to definitively resolve these questions. It cannot land, cannot drill, cannot directly sample the ocean. But it can search for the chemical signatures that would indicate life is possible, and it can identify locations where future missions could search more directly. The Clipper is the first step on a path that could lead to one of the most significant discoveries in human history. The spacecraft has been travelling for months now. Its systems are functioning normally. Its trajectory is precise. Its instruments are ready. Somewhere in the darkness between Mars and Jupiter, the Europa Clipper coasts onward, carrying humanity's question toward a moon that has waited 4 billion years to be asked. The ocean beneath Europa's ice exists because of a force that most people associate with tides on Earth, but operating at a scale and intensity that transforms a frozen moon into a potentially living world. To understand how Europa maintains liquid water so far from the Sun, we must examine the gravitational machinery that keeps its interior warm, a mechanism so elegant and so powerful that it may have been sculpting habitable environments long before Earth even formed. Jupiter is the largest planet in our solar system, containing more mass than all other planets combined. Its gravitational influence extends millions of kilometers in every direction, bending the orbits of asteroids, capturing passing comets, and warping the shapes of any moons that venture close enough. Europa orbits Jupiter at a distance of approximately 671,000 kilometers, completing one orbit every 355 Earth days. At this distance, Jupiter's gravity is strong enough to lock Europa in synchronous rotation, meaning the same face of the Moon always points toward the planet, just as the same face of our Moon always points toward Earth. But synchronous rotation is merely the beginning of Jupiter's influence on Europa. Europa does not orbit Jupiter in a perfect circle. Its orbit is slightly elliptical, and this ellipticity is maintained by gravitational interactions with two other large moons, Io and Ganymede. The three moons are locked in what astronomers call a Laplace resonance, an orbital dance where for every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This precise mathematical relationship means the moons periodically align, with their combined gravity tugging on each other at regular intervals. The resonance prevents Europa's orbit from circularizing over time, maintaining a slight eccentricity that has persisted for billions of years. This maintained eccentricity is the key to Europa's liquid ocean. As Europa moves along its elliptical orbit, its distance from Jupiter varies by approximately 96,000 kilometers between closest approach and farthest retreat. At closest approach, Jupiter's gravity pulls more strongly on the near side of Europa than on the far side, stretching the Moon along the axis pointing toward Jupiter. At farthest retreat, this stretching relaxes slightly. The difference in gravitational pull across Europa's diameter creates tidal forces, the same phenomenon that raises and lowers ocean tides on Earth. But while Earth's tides are measured in meters, Europa's tidal deformation is measured in tens of meters. The entire moon flexes, its solid ice shell rising and falling, its rocky interior compressing and relaxing, its very shape cycling between more elongated and more spherical every 3.55 days. This constant flexing generates heat. The mechanism is analogous to bending a paperclip back and forth. The repeated deformation causes the material to warm. In Europa, the cyclic tidal stressing of rock and ice dissipates energy as heat, warming the moon's interior from within. The process is called tidal dissipation, and on Europa it generates enough heat to maintain a liquid water ocean, beneath a shell of ice that would otherwise be frozen solid at the temperature of 130 degrees below 0 Celsius that prevails at Europa's surface. The amount of heat generated is substantial. Models suggest that tidal heating in Europa produces somewhere between 25 and 90 terawatts of thermal power, depending on assumptions about the moon's internal structure and the thickness of its ice shell. For comparison, all of human civilization currently uses approximately 18 terawatts of power. Europa's interior is being heated at a rate that could power several Earths, and this heating has likely continued for billions of years, maintaining liquid water in the outer solar system for longer than complex life has existed on our planet. But tidal heating is not uniformly distributed throughout Europa. The flexing is most intense at the ice-water interface and at the ocean rock interface at the seafloor. The rocky mantle experiences the greatest stress, and models predict that this stress should be concentrated at certain latitudes and longitudes where the tidal forces align. If Europa's interior is warm enough, and if the tidal stressing is concentrated enough, then the seafloor should experience something that Earth's seafloors experience: volcanism, hydrothermal vents, places where hot, mineral-rich water emerges from cracks in the rock and enters the ocean. On Earth, hydrothermal vents host some of the most extreme and most ancient ecosystems ever discovered. They exist in perpetual darkness, kilometers below the ocean surface, completely independent of sunlight. The organisms that live there derive energy not from photosynthesis, but from chemosynthesis, chemical reactions that extract energy from the mineral-rich water emerging from the vents. Bacteria oxidize hydrogen sulfide, methane, and other volcanic gases, building organic molecules from inorganic ingredients. These bacteria form the base of food chains that include tube worms, blind shrimp, specialized crabs, and other creatures that have never experienced daylight and would die if exposed to it. The discovery of hydrothermal vent ecosystems on Earth revolutionized our understanding of where life can exist. Before their discovery in 1977, most scientists assumed that all complex ecosystems ultimately depended on sunlight. The ocean's depths were thought to be biological deserts, sparse and lifeless below the depth where light penetrates. The discovery of thriving communities around deep-sea vents, communities that owed nothing to the sun and everything to the Earth's internal heat, demonstrated that life could exist wherever liquid water, energy, and chemistry intersected. It suggested that planets and moons far from their parent stars might still harbour life, as long as they had internal heat sources to maintain liquid water and drive chemical reactions. This is why Europa became interesting. If tidal heating can maintain a liquid ocean and drive hydrothermal activity at the seafloor, then Europa might possess all the ingredients for life: liquid water, chemical energy from volcanic vents, and the raw materials carried by asteroid and comet impacts over billions of years. Europa might be running the same experiment that Earth ran 4 billion years ago, the experiment that produced life on our planet within a few 100 million years of conditions becoming suitable. The parallels between early Earth and modern Europa are striking enough that some scientists have suggested we should search for Earth's oldest life forms by studying what survives in the harshest environments our planet offers: the deep ocean vents, the cracks in Antarctic ice where microbes persist in thin films of liquid water, the buried aquifers miles beneath Earth's surface where bacteria have been isolated from the surface biosphere for millions of years. These environments may be the closest analogues we have to conditions beneath Europa's ice. The organisms that thrive there, the extremophils that have adapted to crushing pressure, perpetual darkness, and temperatures that would kill ordinary cells, represent our best guesses for what European life might look like if it exists. The evidence for hydrothermal activity on Europa remains circumstantial but compelling. The Hubble Space Telescope has observed what appear to be water vapour plumes erupting from Europa's surface, suggesting that liquid water from below is occasionally reaching space. If confirmed, these plumes would indicate that the ocean is in contact with the ice shell in ways that allow material to reach the surface, material that could be sampled by a properly designed spacecraft without ever having to drill through kilometres of ice. The Galileo magnetometer data showing an induced magnetic field not only confirms the presence of a global ocean, but suggests the ocean is salty, conducting electricity well enough to respond to Jupiter's rotating magnetic field. Salt implies dissolved minerals, which implies chemical complexity, which implies the kind of soup that might support biology. The ice shell itself provides indirect evidence of activity below. Europa's surface is geologically young, perhaps only 40 to 90 million years old, based on the sparse cratering. Compare this to the Moon, which preserves impact craters from 4 billion years ago because nothing erases them. Europa's surface is being renewed, resurfaced, recycled by processes that smooth away craters and replace old ice with new. The leading hypothesis is that warmer ice from below rises toward the surface while colder ice sinks, a process called convection, or alternatively that liquid water from the ocean occasionally breaches the ice shell and floods the surface before refreezing. Either process suggests an active, dynamic world where the ocean and the ice interact in complex ways. The most tantalizing features on Europa's surface are the so-called chaos terrain, regions where the ice appears to have broken into rafts that floated, rotated and refroze in new configurations, like pack ice on an Arctic sea. Some chaos regions resemble what you would see if you took a photograph of sea ice, broke it into pieces, shuffled the pieces, and then photographed it again. The original pattern is disrupted, shifted, fragmented. The simplest explanation is that these regions once had liquid water at the surface, water that allowed the ice to move freely before it refroze. Whether this water came from local melting of the ice shell or from direct contact with the ocean below remains debated. But either interpretation suggests that Europa's ocean is not a static, isolated reservoir. It interacts with the ice above in ways that might carry chemical signatures from the deep to the surface. If hydrothermal vents exist at Europa's seafloor, they would provide the same ingredients that support life at Earth's deep sea vents: hot water, dissolved minerals, and chemical gradients that can be exploited for energy. The key chemical reactions involve the interaction of water with freshly exposed rock, a process called serpentinization. When ocean water percolates through cracks in hot basaltic rock, the rock reacts with the water to produce hydrogen gas and methane, along with various metal sulfides and other compounds. These chemicals represent stored energy, energy that can be released by organisms that know how to tap it. On Earth, entire ecosystems run on the energy generated by serpentinization. There is no reason in principle why the same process could not occur on Europa. The depth of Europa's ocean, estimated at somewhere between 60 and 150 kilometres, would create pressures at the seafloor far greater than anything found on Earth. The deepest point in Earth's oceans, Challenger Deep in the Mariana Trench, reaches approximately 11 kilometres, with a pressure of about 1,000 atmospheres. Europa's seafloor, if the ocean is 100 kilometres deep, would experience pressures exceeding 1,400 atmospheres. Life on Earth has been found at Challenger Deep, microbes and even small invertebrates that have adapted to the crushing pressure, but we have no examples of life at 400 atmospheres. Whether life could adapt to such extremes remains unknown. The pressure would fundamentally alter protein chemistry, cell membrane structure, and the behaviour of water itself. Life might find a way, or it might not. The temperature gradient within Europa's ocean also presents puzzles. If the ocean is in direct contact with a warm rocky seafloor heated by tidal forces, the bottom waters might be significantly warmer than the top, perhaps by tens of degrees. On Earth, deep-sea vents can reach temperatures of 350 degrees Celsius or higher, though the surrounding water remains cold because the heat dissipates rapidly. Europa's ocean, trapped beneath an insulating ice shell with no weather and no currents driven by sunlight, might stratify differently. The warmest water might stay near the bottom, creating stable layers that could persist for millions of years. Or convection currents might mix the ocean thoroughly, distributing heat and chemicals throughout its volume. We do not know which scenario is correct. The Europa Clipper's ice-penetrating radar will attempt to probe the structure of the ice shell, potentially revealing information about how heat moves through the system. The possibility that life exists on Europa right now, at this moment as you hear these words, is not science fiction. It is a testable hypothesis based on our understanding of how life originated on Earth, what conditions it requires, and what environments Europa provides. The hypothesis might be wrong. Europa's ocean might be sterile, a vast volume of salty water sitting in darkness for billions of years, all the ingredients for life present but never combining into anything that could reproduce, evolve, or be called alive. Or the hypothesis might be right. Somewhere in the black depths beneath that ice, organisms might be swimming, crawling, metabolizing, dying, and being consumed by other organisms. A biosphere entirely independent of Earth, never touched by sunlight, never aware of the universe beyond its frozen ceiling. The possibility is not remote. It is plausible enough that NASA has spent nearly $5 billion building a spacecraft to investigate it. $5 billion represents a national commitment, a collective bet that the question is worth asking with the best tools we can build. The Europa Clipper will spend approximately 4 years in the Jupiter system, executing 49 close flybys of Europa, mapping the surface, analysing the ice, searching for plumes, measuring the magnetic field, listening to the tidal flexing, gathering data from every angle its instruments can achieve. Each flyby will carry the spacecraft to within 25 kilometres of Europa's surface at closest approach, threading the needle between the radiation belts that surround Jupiter and the ice shell that hides the ocean. The radiation environment is one of the mission's greatest challenges. Jupiter's magnetic field is enormous, extending millions of kilometres into space and trapping energetic particles that spiral along magnetic field lines like streams of invisible fire. Europa orbits within the most intense radiation zone, a region where unshielded electronics would fail within hours, and unprotected humans would receive a lethal dose within minutes. The Clipper carries a radiation vault, a carefully designed enclosure with walls made of titanium and tantalum that shield the most sensitive components from the worst of the bombardment. Even so, the spacecraft is designed to spend as little time as possible in the most intense radiation zones, swooping in for close flybys and then retreating to safer distances to process and transmit data before the next approach. The orbital mechanics are choreographed with extraordinary precision. Each flyby is designed to achieve specific science objectives while protecting the spacecraft from cumulative radiation damage. Some flybys will pass over Europa's equator, others over its poles. Some will occur when Europa is between Jupiter and the Sun, allowing for backlit observations of potential plumes. Others will occur when the Sun is behind the spacecraft, enabling high-resolution imaging of surface features. The 49 flybys will build up a comprehensive dataset covering essentially the entire Moon, achieving an intimate familiarity with Europa that would have seemed impossible just decades ago. The instruments aboard the Clipper are designed to work in concert, each one contributing pieces to a puzzle that no single measurement could solve. The mass spectrometer will identify molecules in Europa's thin atmosphere and any plume material the spacecraft encounters. If complex organic molecules are present, molecules that could serve as building blocks for life, the spectrometer will detect them. If simple gases like hydrogen, methane, or hydrogen sulfide are escaping from the ocean, the spectrometer will measure their abundances and isotopic compositions. The ultraviolet spectrograph will examine how different materials on Europa's surface reflect and absorb ultraviolet light, revealing information about their chemical composition. The thermal emission imaging system will map surface temperatures with sufficient precision to identify warm spots that might indicate recent activity. The ice-penetrating radar is perhaps the instrument most likely to reveal revolutionary information about Europa's habitability. By transmitting radio waves through the ice and analysing the reflected signals, the radar can detect layers, voids, and boundaries within the ice shell. It might reveal pockets of liquid water trapped within the ice, lakes analogous to the subglacial lakes found beneath Antarctic ice sheets on Earth. It might reveal the interface between ice and ocean, measuring the thickness of the shell at different locations. It might reveal structures that no one has anticipated, features of a world that operates according to rules we have not yet learned. The radar cannot see the ocean itself in detail, but it can characterize the boundary layer where ice meets water, and that boundary is where the most accessible potential biosignatures might be found. The Europa Clipper's mission is not to find life directly. The spacecraft carries no instruments capable of detecting living organisms. It carries no microscopes, No life detection experiments in the classical sense, no instruments designed to answer the question, is something alive in this sample? What the Clipper can do is determine whether Europa's ocean is habitable, whether the chemistry is conducive to life, whether the energy sources exist that life would need, whether materials from the ocean reach the surface where future missions could sample them. The Clipper is a reconnaissance mission, a scout sent ahead to determine whether the territory is worth exploring more intensively. If the Clipper's findings suggest that Europa is indeed habitable, that the ocean has the right chemistry and energy sources, that plumes or surface materials provide access to ocean water without drilling through kilometres of ice, then the next mission will be designed specifically to search for life. Concepts are already being studied. A Europa lander could touch down near a recently active region, sample the surface ice, and analyse it for organic molecules, cellular structures or other biosignatures. A more ambitious concept involves a spacecraft that could melt through the ice shell and release a robotic submarine into the ocean below. Such a mission remains decades away and would cost tens of billions of dollars, but it is technically conceivable. The ice shell, while thick, is not impenetrable. Heat and patience could breach it. The question of whether we are ready for the answer lurks beneath the surface of every discussion about searching for life on Europa. If life is found, what then? How would the discovery be announced? How would different cultures, religions, and philosophical traditions respond? Would it matter if the life was simple, just microbes, or would only complex, intelligent life provoke a genuine shift in human self-understanding? Would finding life on Europa be cause for celebration, for fear, for religious crisis, or for a kind of cosmic humility that transcends any single response? These questions cannot be answered in advance. But they are not merely philosophical exercises. The Europa Clipper is real. It is travelling toward Jupiter at this moment. Its instruments are ready. Its trajectory is committed. Within a decade, we will have data that speaks to questions that humans have asked for millennia. The machinery is in motion. The question has been cast into the void, and the void will answer. The ice beneath which Europa's ocean hides is not a passive barrier. It is an active membrane, a dynamic layer that interacts with the ocean below and the radiation environment above. Understanding this ice is essential to understanding what might live beneath it. The ice shell of Europa is unlike any frozen surface in our everyday experience. When we think of ice, we imagine the brittle substance that forms on winter ponds, the cubes that chill our drinks, the glaciers that carve mountain valleys. But Europa's ice exists under conditions so extreme that it behaves in ways that challenge our intuition. The surface temperature hovers around negative 260 degrees Fahrenheit, so cold that the ice becomes harder than granite, as rigid as bedrock. At these temperatures, water ice would shatter like glass under impact rather than crack or deform. Yet this same ice, under the immense pressures and warmer temperatures found deeper within the shell, becomes plastic and malleable, flowing like warm caramel over geological timescales. This gradient from brittle surface to ductile interior creates a shell with complex mechanical properties. The upper portion, perhaps the top few kilometres, forms a rigid lid that cracks and fractures under stress. The deeper portions flow in response to the same stresses, convecting slowly like the mantle of a planet, carrying heat from the ocean below toward the frigid surface above. Between these two layers may exist a transition zone where the ice is neither fully rigid nor fully flowing, where meltwater might accumulate in lenses and pockets, forming a hidden plumbing system within the shell itself. The chaos terrains that scar Europa's surface are thought to be surface expressions of this deep convection. In certain regions, warmer ice from below rises toward the surface, while colder, denser ice sinks to take its place. This overturn disrupts the surface, breaking it into blocks that rotate, tilt, and refreeze into the jumbled landscapes that Galileo photographed. The process is slow by human standards, requiring thousands to millions of years to create the features we observe. But it is fast by geological standards, indicating that Europa's interior remains thermally active, that heat continues to flow, that the engine driving this world's geology has not wound down. The ridges that crisscross the surface tell a different story of ice dynamics. These paired ridges, running for hundreds of kilometres across the moon, form along fractures in the ice where the shell repeatedly cracks open and refreezes. As Europa orbits Jupiter, the tidal stresses wax and wane, pulling the ice shell apart along certain orientations and compressing it along others. fractures open slightly during certain portions of the orbit, allowing warm, briny water or vapour to rise into the gap. As the orbit progresses and the stresses shift, the fractures close again, squeezing the newly frozen material and pushing it upward along both sides of the crack. Over thousands of orbital cycles, this repeated opening and closing builds the twin ridges that characterise Europa's appearance, each ridge recording countless tidal pulses like the rings of an ancient tree recording countless seasons. Some of these ridges show evidence of having formed along fractures that penetrate entirely through the ice shell to the ocean below. The material deposited along these cracks includes substances that appear different from pure water ice, materials that may have been dissolved in the ocean water before it froze upon reaching the vacuum of space. If these interpretations are correct, then some of Europa's ridges mark places where ocean water has breached the surface within the geologically recent past. The surface ice in these regions would contain ocean-derived materials, compounds that might include salts, organics, and whatever else the ocean contains. These ridges could serve as natural drill cores, sampling locations where future missions might access ocean chemistry without needing to penetrate the full thickness of the shell. The double ridges are one of Europa's most distinctive features, yet their formation mechanism remained poorly understood until recently. In 2022, researchers studying ice-penetrating radar data from Greenland discovered remarkably similar structures forming in the ice sheet above subglacial water pockets. The ridges formed when water infiltrated the ice from below, refroze, expanded, and fractured the overlying ice. This process, observed happening on Earth over timescales of years to decades, produced features geometrically similar to Europa's ridges, suggesting that liquid water shallow beneath the surface may be integral to ridge formation. The implication is profound. If Europa's ridges form the same way, then liquid water exists not just 90 miles down in the ocean, but perhaps only a few kilometres below the surface in numerous locations. The ice shell would then be permeated with aqueous environments, cells within cells, water within water, creating multiple potential habitats rather than a single distant ocean. The possibility of shallow water bodies within the ice shell has dramatic implications for habitability and for future exploration. Life that evolved in the ocean might colonize these shallow environments, riding plumes of rising warm water into the ice above, adapting to the different conditions found in these trapped lakes. Some of these shallow reservoirs might be more habitable than the deep ocean itself, receiving heat from below while remaining protected from radiation by kilometres of overlying ice, but existing at pressures and temperatures more compatible with the biochemistry we understand. If material from these shallow bodies occasionally reaches the surface during eruption, events, or chaos terrain formation, then biosignatures might be sprinkled across Europa's ice without requiring any organism to survive the extreme conditions of the surface itself. The radiation environment at Europa's surface deserves careful consideration, for it shapes what might survive there and what evidence might persist. Jupiter's immense magnetic field accelerates charged particles to tremendous energies, channeling them into radiation belts that dwarf anything found around Earth. Europa orbits within these belts, bathed in a continuous flux of energetic electrons, protons, and heavier ions that bombard its surface with the intensity of a perpetual nuclear accident. The radiation dose at Europa's surface is lethal on timescales of minutes. Any unprotected cell, any organic molecule exposed to this environment would be systematically dismembered by the relentless particle bombardment. The chemical bonds that hold molecules together cannot withstand the continuous ionizing assault. This radiation creates a surface that is chemically active despite the extreme cold. Water ice molecules are broken apart, creating fragments that recombine into new compounds. Hydrogen peroxide forms. Sulfur compounds oxidize. Organic molecules, if present, are radialized into simpler fragments or polymerized into complex radiation-resistant residues. The surface is a chemistry experiment conducted under conditions no laboratory on Earth can replicate, running continuously for billions of years. But the radiation does not penetrate deeply. The ice itself provides shielding. Within a metre of the surface, the radiation dose drops by orders of magnitude. Within a few metres, it becomes negligible. Any material transported from the ocean that reaches the near-surface environment, but remains buried beneath even a thin layer of ice, would be protected from the worst radiation damage. Fresh fractures, recent plume deposits, and the undersides of overturned ice blocks could harbour materials that have not been completely degraded by radiation. The Clipper's mass spectrometers might detect molecules in Europa's tenuous atmosphere that originated from such protected environments, compounds that would not survive exposure to surface radiation, but could persist in the vapour released from recently exposed ice. The interplay between protection and destruction creates a kind of timer for biosignature survival. Material from the ocean that reaches the surface begins to degrade immediately. Over thousands of years, radiation processing destroys most diagnostic features. Over millions of years, little remains but the most radiation-resistant compounds. But if material is continuously being delivered from below, through plumes, through fractures, through the slow overturn of the ice shell, then fresh material might always be available somewhere on the surface. The question becomes one of timing and location. Can we identify where fresh material has recently appeared? Can we reach those locations before radiation has erased the evidence? The Clipper's imaging campaigns will map the surface in unprecedented detail, potentially identifying the youngest terrains, the most recently active regions, the places where ocean material most recently breached the ice. The extreme antiquity of Europa's ocean raises questions that do not arise when considering life on Earth. Our ocean has existed for over 4 billion years, enough time for life to emerge and evolve into the staggering diversity we observe today. But Europa's ocean may have existed for equally long. Tidal heating from Jupiter has likely operated since the Moon's formation, maintaining liquid water beneath the ice for the entire history of the solar system. If life can emerge from the right chemistry given enough time, then Europa has had enough time. 4 billion years of liquid water, chemical energy from water-rock reactions, molecular building blocks delivered by comets and produced by radiation chemistry. The ingredients and the time are both present. What remains unknown is whether the recipe is correct. The conditions under which life first arose on Earth remain one of science's great unsolved mysteries. We know that life was present by 3.5 billion years ago, perhaps earlier. We know it arose from non-living chemistry through some series of steps that produce self-replicating, metabolizing systems from simpler precursors. But we do not know the specific pathway, the exact sequence of events, the necessary conditions. Multiple theories exist, each with supporting evidence, none definitively proven. Life may have begun at hydrothermal vents on the ocean floor where chemical gradients provided energy and minerals provided catalysts. Life may have begun in warm, shallow pools, where evaporation concentrated organic compounds and ultraviolet radiation drove chemical reactions. Life may have begun beneath ice, where the concentration of solutes in liquid water pockets and the stabilization of complex molecules by cold temperatures created favorable conditions. Life may have begun in some environment that no longer exists, erased by the subsequent evolution of the planet. Without knowing how life began on Earth, we cannot confidently predict whether it would begin on Europa. The hydrothermal vent hypothesis holds particular relevance for Europa because similar environments almost certainly exist on that moon. Where water contacts hot rock on the ocean floor, chemical reactions are inevitable. Iron and magnesium silicates react with water to produce hydrogen gas and heat. Sulfur compounds dissolve and precipitate. Minerals form chimneys and structures around the vents. On Earth, these environments host some of the most extreme and ancient forms of life. Organisms that derive all their energy from chemistry, that live their entire lives in complete darkness, that have no dependence whatsoever on sunlight. These chemosynthetic ecosystems prove that life can thrive without a star, that an ocean can be habitable even beneath permanent ice, that energy from geology can substitute for energy from photosynthesis. The discovery of hydrothermal vent ecosystems on Earth in 1977 revolutionized our understanding of where life could exist. Before that discovery, scientists assumed that all ecosystems ultimately depended on photosynthesis, that sunlight was the universal source of biological energy. The vents shattered that assumption, revealing a shadow biosphere that had existed in darkness for billions of years, completely independent of the sun-driven surface world. Giant tube worms, their tissues packed with symbiotic bacteria that harvested chemical energy from hydrogen sulfide. Eyeless shrimp grazing on bacterial mats that grew on mineral surfaces. Entire food webs sustained by the heat and chemistry of the planet's interior rather than by light from the sky. If such ecosystems could exist on Earth, undetected until humans developed the technology to explore the deep ocean, then similar ecosystems could exist on Europa, awaiting only the technology to find them. The tube worms of Earth's hydrothermal vents offer a striking example of life's adaptability to extreme environments. Riftia pachyptila, the giant vent worm, can grow to over 2 meters in length, thriving in water heated to temperatures that would cook most organisms. These worms have no mouth, no gut, no digestive system at all. Instead, they house trillions of chemosynthetic bacteria within their tissues, providing the bacteria with chemicals from the vent water, while receiving organic compounds in return. The worms are essentially farming bacteria inside their own bodies, their red plumes extracting oxygen and hydrogen sulfide from the water, their blood delivering these chemicals to the bacterial colonies within. This intimate symbiosis between animal and microbe represents a fundamentally different way of being alive, one that does not require photosynthesis, plates, or the world above. Could something analogous exist on Europa? The honest answer is that we do not know. We cannot know until we look. The chemistry appears plausible, the energy sources appear adequate, the time has been sufficient. But the gap between possibility and actuality cannot be bridged by theory alone. Only observation can answer whether Europa's ocean hosts the equivalent of tube worms, or bacterial mats, or nothing at all. The Europa Clipper cannot see through 90 miles of ice to photograph the ocean floor. But it can characterize the ocean's chemistry, determine whether the necessary ingredients are present, identify whether materials from the ocean reach accessible locations. Each finding will either strengthen or weaken the case for life, narrowing the range of possibilities until a direct search becomes either irresistible or unnecessary. The composition of Europa's ocean remains uncertain, and this uncertainty encompasses wide possibilities. The ocean might be relatively fresh, similar to Earth's ocean in salinity, or it might be hypersaline, so concentrated with dissolved minerals that familiar biochemistry could not function. It might be acidic, alkaline, or neutral. It might contain dissolved gases that would be toxic to Earth life, or dissolved nutrients that would be familiar. The Clipper's instruments will constrain these possibilities, measuring the composition of materials ejected into space, analysing the surface ice that derives from the ocean below, modelling the chemical evolution of an ocean in contact with a silicate seafloor for billions of years. The presence of magnesium sulfate salts has been inferred from spectroscopic observations, the same compound found in Epsom salts on Earth. Sodium chloride, ordinary table salt, has also been detected, its yellowish deposits visible in infrared observations of the chaos terrains. The reddish-brown material that colours parts of Europa's surface may contain sulfur compounds, either delivered from EO or produced by radiation processing of native sulfur. These observations suggest an ocean with complex chemistry, not pure water, but a brine containing dissolved minerals with concentrations that remain poorly known. The pH of the ocean, its acidity or alkalinity, affects what chemistry can occur and what life could tolerate. Earth organisms span a remarkable range of pH tolerance, from bacteria that thrive in battery acid to those that live in caustic soda, but the biochemistry common to all Earth life functions best in a relatively narrow range around neutral. If Europa's ocean falls outside that range, life there would need different biochemistry, different enzymes, different molecular strategies. Such life might be completely invisible to detection methods designed to find Earth-like biology. We might be searching for the wrong signatures, looking for amino acids when we should be looking for something our chemistry has never imagined. The question of alternative biochemistries opens into one of astrobiology's deepest uncertainties. All life on Earth shares common features, because all life on Earth shares common ancestry. We use the same genetic code, the same set of amino acids, the same basic metabolic pathways, because we are all descended from a single origin event. But we have no way of knowing whether these features are inevitable consequences of chemistry or historical accidents frozen in place by the constraints of inheritance. Life elsewhere might use different amino acids, different genetic molecules, different approaches to storing energy and information. Such life might be chemically unrecognizable, invisible to instruments designed to detect familiar biosignatures. The Europa Clipper's instrument suite was designed with this uncertainty in mind. Rather than searching only for specific molecules associated with Earth life, the instruments will characterize general chemical complexity. They will look for concentrations of organic compounds beyond what non-biological processes typically produce. They will look for patterns of molecular weights that suggest biological synthesis. They will look for isotopic ratios that indicate metabolic activity. These approaches cast a wider net than searching for specific biomarkers, increasing the chance of detecting unfamiliar biology if it exists. The mass spectrometers aboard the Clipper can identify molecules by their mass, measuring the precise weight of particles entering the instrument and matching them against databases of known compounds. But they can also identify unknown compounds, molecules that match no entry in any database, substances that exist nowhere on Earth. If the Clipper detects such molecules in Europa's environment, especially complex organic molecules that seem difficult to produce through purely geological processes, the discovery would demand explanation. It might indicate exotic chemistry driven by radiation and mineral catalysis. Or it might indicate something more profound, the chemical signatures of an ecosystem operating by rules we have not yet learned. The detection of amino acids would be particularly significant, though not conclusive. These molecules, the building blocks of proteins, form readily in space in carbonaceous meteorites, in laboratory simulations of interstellar conditions. Their presence on Europa would not prove life exists. But the pattern of which amino acids appear, their relative abundances, whether they show chirality or handedness, could distinguish biological from non-biological origins. Earth life uses almost exclusively left-handed amino acids, a bias that non-biological synthesis does not produce. If Europa's amino acids show similar chirality, it would suggest biological manufacture. If they show no chirality, it would suggest geological sources. The distinction matters, and the Clipper's instruments have the sensitivity to potentially make it. The organic compounds detected at Europa's surface so far remain difficult to interpret. Some observations suggest the presence of formaldehyde, formic acid, and other simple organics. Whether these compounds derive from the ocean, from meteoritic delivery, from radiation processing of surface ices, or from some combination of sources remains unclear. The Clipper will make measurements in the near-surface environment and in any plumes it encounters, sampling material that has more recently emerged from the interior and has suffered less radiation damage. These measurements will provide cleaner signals, less contaminated by surface processing, more directly reflecting the composition of materials beneath the ice. The possibility of plume sampling represents one of the Clipper mission's most tantalizing opportunities. When Cassini flew through the plumes of Enceladus, it detected complex organic molecules, molecular hydrogen, and silica nanoparticles, all consistent with hydrothermal activity on the seafloor. Those single flybys through Enceladus's plumes revolutionized our understanding of that moon's habitability. Similar measurements at Europa, through multiple passes at closer range with more capable instruments, could provide even more detailed information about ocean chemistry. But the plumes at Europa, if they exist at all, are far more tenuous than those at Enceladus. Enceladus's geysers eject hundreds of kilograms of material per second, creating dramatic jets visible from orbit and producing a significant ring of particles around Saturn. The possible plumes detected at Europa by Hubble appear to be intermittent and less voluminous, perhaps ejecting only a few kilograms per second during active phases. The Clipper's instruments are designed to detect these fainter signals, but the spacecraft might need to be fortunate in its timing, flying through regions where activity is occurring at that moment. The mission's many flybys increase the odds of such fortune. Over 4 years and dozens of close approaches, the statistical likelihood of encountering active plumes, if they exist with any regularity, becomes substantial. The dust analyzer aboard the Clipper deserves particular attention as a potential biosignature detector. This instrument captures individual particles, measures their mass, and vaporizes them for chemical analysis. When dust grains strike the instrument's target at speeds of several kilometers per second, they instantaneously vaporize along with a small amount of target material. The resulting plasma contains ions that can be separated by mass and identified. At Enceladus, a similar instrument detected organic molecules with masses exceeding 200 atomic mass units, molecules too large and complex to form easily through simple chemical reactions. If the Clipper's dust analyzer detects similar high-mass organics in particles from Europa's plumes, or from dust lifted from the surface, the discovery would demand serious consideration of biological sources. The difference between intriguing chemistry and confirmed biology remains vast, and the scientific community has been burned before by premature claims of life detection. The 1996 announcement that a Martian meteorite contained fossilized bacteria generated worldwide excitement, followed by decades of controversy. The structures initially interpreted as microfossils were eventually explained by most researchers as mineral formations. The magnetic crystals suggested as bacterial products could be produced geologically. The organic compounds were largely contamination from Earth. The lesson of ALH, 84001 as the meteorite is designated, remains fresh in the minds of astrobiologists. Extraordinary claims require extraordinary evidence. The bar for announcing the detection of extraterrestrial life is set deliberately high. The Europa Clipper will not clear that bar. It is designed to assess habitability, not to find life. But it will determine whether clearing that bar is worth attempting, whether the evidence justifies the immense investment of a life detection mission, whether Europa is the place where humanity should focus its search for cosmic company. The Clipper's instruments will paint a detailed portrait of Europa's ocean, its chemistry, its dynamics, its potential. From that portrait, scientists will judge whether the canvas is blank or whether something might be painted upon it that we cannot yet see. The portrait that emerges from the Clipper's data will answer questions that scientists have been asking for decades, but it will simultaneously generate new questions that no one has yet thought to pose. This is the nature of exploration at the frontier. Every answer is also a doorway. Every resolution reveals deeper mysteries waiting beyond. The instruments currently travelling toward Jupiter at 30,000 miles per hour carry within them the capacity to transform our understanding of where life can exist, and that transformation will ripple outward through every field of human inquiry. Consider what it means for life to emerge from nothing. On Earth, this transition happened quickly. Within a few 100 million years of our planet's formation, perhaps within just tens of millions of years after conditions became even marginally tolerable, the first primitive cells appeared. The rapidity of this emergence has long puzzled scientists. Either the origin of life is cosmically easy, requiring only the right conditions and sufficient time to occur with near certainty, or Earth was extraordinarily lucky, winning a 1,000,000,000-to-1 lottery that most planets lose. For decades, these two possibilities have remained balanced, with evidence insufficient to distinguish between them. Europa offers a way to break that tie. If life arose independently in Europa's ocean, if the same fundamental transition from chemistry to biology occurred twice within a single solar system, the implications are staggering. The universe would effectively be proven teeming with life. If the same outcome occurred twice in one small neighbourhood, it must occur billions upon billions of times across the galaxy. The equations of probability would demand it. Every star with planets in the right zones, every moon with liquid water beneath its surface, every comet with organic molecules drifting through interstellar space, all of them become candidates for hosting the same miraculous transition that occurred here and there. The loneliness that humanity has assumed as its cosmic birthright would be revealed as illusion. But the opposite result carries equal weight. If Europa's ocean has remained sterile for 4 billion years despite having all the apparent ingredients for life, something in our understanding is fundamentally wrong. Perhaps life requires conditions we have not imagined. Perhaps the spark that ignites biology is rarer than our theories suggest. Perhaps Earth's quick emergence was indeed a lottery win of almost unfathomable improbability, and we exist as the singular exception in a universe that otherwise remains forever dead. This too would be a profound discovery, reshaping our understanding of our place in existence. The Clipper mission is designed to provide the evidence that will eventually lead toward one of these conclusions, not through direct detection of the life, but through the accumulated weight of observations about Europa's habitability. If the ocean proves chemically active, if energy sources flow constantly from the seafloor, if organic molecules concentrate in ways that suggest complex chemistry, the case for a life detection mission becomes overwhelming. If instead the ocean proves stagnant, its chemistry frozen in equilibrium, its potential unrealized, we will know that the mere existence of water is insufficient. The thermal imaging that the Clipper will conduct represents one of the most straightforward ways to assess this question. Heat flow tells a story. On Earth, hydrothermal vents are not randomly distributed across the seafloor. They cluster along mid-ocean ridges where tectonic plates spread apart, along subduction zones where one plate slides beneath another, along hotspots where mantle plumes rise toward the surface. The geography of heat maps the geology of activity. Europa's thermal map will reveal whether similar concentrations exist, whether the tidal heating that keeps the ocean liquid manifests uniformly across the globe, or concentrates in specific regions where conditions might favour the emergence and persistence of life. The spacecraft's thermal instrument can detect temperature variations as small as a fraction of a degree Kelvin from orbit. This sensitivity allows it to identify regions where heat flows more freely from the interior, where the ice shell may be thinner, where warm water may approach closer to the surface. These warm spots, if they exist, would be prime targets for future missions. They would represent the places where the ocean's secrets are most accessible, where the ice barrier separating us from whatever lies beneath is at its minimum thickness. But the thermal mapping also serves a more immediate purpose. It helps scientists understand the mechanics of the ice shell itself, the way heat moves through this complex barrier, the way the shell responds to the constant flexing imposed by Jupiter's gravity. The ice shell is not passive. It does not simply sit there, frozen and unchanging, while the ocean beneath it goes about its business. The shell participates in the moon's thermal budget, conducting heat from the warm interior to the cold surface, radiating that heat into the vacuum of space. The efficiency of this conduction determines the thickness of the ice, the vigour of any convection within it, the possibility of material exchange between surface and ocean. Understanding this ice shell has occupied planetary scientists for decades because it represents the barrier between everything we can observe and everything we want to know. Surface observations tell us what happens at the top of the shell. Gravity measurements tell us about the mass distribution throughout the moon. Magnetic field measurements tell us about the conducting ocean beneath. But the shell itself, this kilometres-thick layer of ice that may or may not include pockets of liquid, that may or may not circulate through convection, that may or may not allow material to travel between surface and ocean, this shell remains the great unknown. The ice-penetrating radar aboard the Clipper will peer into this unknown with unprecedented clarity. Radar waves at the frequencies the Clipper will use can penetrate ice to depths of potentially 20 kilometres or more, depending on the ice's temperature and purity. As these waves travel downward, they reflect off boundaries between different materials, between ice and rock, between solid ice and liquid water, between ice at different temperatures or with different compositions. By measuring the timing and strength of these reflections, scientists can construct three-dimensional maps of the ice shell's internal structure. This technique has been used extensively on Earth's ice sheets. Radar surveys of Antarctica and Greenland have revealed subglacial lakes, buried rivers of meltwater, ancient meteorite craters hidden beneath kilometres of accumulated ice. The technology is proven. What remains unknown is what it will show at Europa. The possibilities span a remarkable range. At one extreme, the radar might reveal an ice shell that is essentially uniform, solid ice from top to bottom, with only the most minor internal variations. This would suggest a relatively simple thermal structure, a moon whose interior heat flows steadily upward through a passive conductive shell. Such a finding would not necessarily preclude life in the ocean below, but it would suggest a limited exchange between surface and interior, making the surface chemistry less relevant to ocean habitability. At the other extreme, the radar might reveal an ice shell riddled with complexity. Pockets of liquid water at various depths, vertical structures suggesting material moving upward or downward through the shell, horizontal layers indicating different episodes of formation or modification, concentrated regions of briny ice created when salty water freezes. Each of these features would tell a story about the moon's history and dynamics, about the way material and energy move through this frozen barrier. The chaos terrains that scar Europa's surface hint at what the radar might find. These regions of jumbled, disrupted ice appear to have formed when sections of the surface collapsed, rotated and refroze in new configurations. One leading hypothesis suggests that these chaotic regions mark places where relatively warm, perhaps liquid, bodies of water existed within the ice shell at shallow depths. As this water refroze or drained away, the surface above lost its support and collapsed into the resulting void. If this interpretation is correct, the radar should detect similar structures forming today. The timescales of ice shell dynamics are slow by human standards, but fast by geological ones. Features that formed thousands or millions of years ago might still be visible as subtle radar reflectors. Active processes occurring now might be detected as changes between successive radar observations. The Clipper's 4-year primary mission provides a baseline for detecting such changes, though the most dramatic dynamics might require longer observation periods. The magnetometer aboard the Clipper will contribute its own lines of evidence to this emerging picture. Magnetic fields respond to electrical currents, and electrical currents flow through conductive materials. Europa's ocean, salted with enough dissolved minerals to conduct electricity, responds to Jupiter's rotating magnetic field by generating its own induced magnetic field. The strength and geometry of this induced field depend on the ocean's conductivity, its depth, and its thickness. Galileo measured this induced field during its flybys and confirmed the ocean's existence. The Clipper will measure it with far greater precision across far more locations, building a global map of how the field varies from place to place. Variations in the induced field strength could indicate variations in ocean properties. Regions where the field is stronger might have deeper or more conductive ocean waters. Regions where the field is weaker might have thinner ocean layers or lower salt concentrations. These measurements complement the other observations in crucial ways. The gravity data tell us about total mass distribution. The radar tells us about ice shell structure. The magnetometer tells us about the conducting ocean that produces the induced field. Together, these datasets can be combined into integrated models of Europa's interior structure, models that account for all the observations simultaneously and reveal the Moon's three-dimensional anatomy. The chemistry of the surface, measured by the spectrometers, adds another dimension to these structural observations. Where the structure of the ice shell allows material from the ocean to reach the surface, the chemistry should reflect that oceanic source. Where the surface has remained isolated from the interior, its chemistry should reflect primarily external processes, radiation bombardment, micrometeorite impacts, and whatever material was originally incorporated when the surface ice formed. By correlating chemical observations with structural observations, scientists can begin to trace pathways through the ice shell. If a particular chemical signature appears most strongly in regions where the radar shows shallow subsurface reflectors, or where the thermal instrument detects enhanced heat flow, this correlation suggests that material has indeed travelled from depth to surface. If instead the chemistry appears uniformly distributed with no relationship to internal structure, this pattern suggests surface-dominated processes with little connection to the ocean below. The integration of all these datasets represents one of the Clipper mission's greatest challenges and greatest opportunities. No single measurement will answer the question of Europa's habitability. Each instrument sees one aspect of a complex system. Only by combining all the measurements, by forcing models to account for all the observations simultaneously, can scientists construct a coherent picture of what Europa is and what it might harbour. This process of integration will take years. The raw data returned by the Clipper will stream back to Earth in enormous quantities, terabits of information describing every aspect of the Moon that the instruments can measure. Teams of scientists will process this data, calibrate it, validate it, and begin the long process of analysis. Papers will appear describing individual observations. Controversies will erupt over interpretations. Hypotheses will be proposed, tested against the data, and either confirmed or rejected. From this scientific ferment will eventually emerge consensus, or at least as much consensus as scientists ever achieve. The picture of Europa that emerges from the Clipper's observations will become the foundation for the next generation of missions, the basis for decisions about where to land, how deep to drill, what to search for. Every subsequent mission to Europa will stand on the shoulders of the Clipper's reconnaissance. The timeline of this process deserves contemplation. The Clipper launched in October 2024 and will not arrive at Jupiter until 2030. Its primary mission will then span 4 years, concluding in 2034. The data analysis will continue for years after that, with major synthesis publications likely appearing in the late 2030s. Any follow-on mission, such as the lander concepts that have been studied, would need years of development after the Clipper's results demonstrate where and how to land. A Europa lander might not launch until the 2040s and would not arrive until the 2050s. This decades-long timeline reflects the realities of deep space exploration. The distances are vast, the engineering is complex, the resources are limited. Every step builds on the previous one, and rushing leads to failure. The journey to understand Europa is not a sprint but a relay race across generations. Scientists who helped design the Clipper's instruments may not live to see the final answer to the question their work addresses. Yet this multi-generational timescale also carries a certain grandeur. The Clipper mission connects the present to a future that remains unwritten. The data it collects will be studied by scientists who are children today. The questions it answers will inform decisions made by people who have not yet been born. The knowledge it generates will become part of humanity's permanent understanding of the cosmos, cited and built upon for centuries to come. This is the nature of fundamental scientific exploration. It transcends individual careers and individual lifetimes. The astronomers who first turned telescopes toward Jupiter's moons 4 centuries ago could not have imagined the missions that would eventually visit those moons. The scientists who struggled to explain Voyager's first images of Europa could not have known that their work would lead to the massive spacecraft now travelling through interplanetary space. The researchers who pore over Clipper data in the coming decades cannot predict what missions their work will inspire or what discoveries those missions will make. The question of life in Europa's ocean connects to the deepest questions humans have ever asked. Are we alone? Did life arise once or many times? Is consciousness a cosmic commonplace or a singular miracle? These questions have been posed in various forms by every human culture, explored by philosophers and theologians, pondered by scientists and poets. The Clipper mission does not pretend to answer them directly. It pretends only to gather evidence, to reduce uncertainty, to constrain the possibilities. But evidence accumulates, constraints tighten, possibilities narrow toward truth. The slow process of scientific investigation, conducted across generations by thousands of researchers using billions of dollars of equipment, gradually reveals the nature of reality. What seems unknowable today becomes known tomorrow. What seems beyond reach becomes grasped. The universe yields its secrets reluctantly, but it yields them. The ocean beneath Europa's ice has kept its secrets for 4 billion years. No eye has ever perceived it. No instrument has ever measured it directly. It has existed in darkness absolute, sealed away from the rest of the solar system by a shell of ice that would seem impenetrable by any natural process. Yet natural processes may have penetrated it nonetheless. The plumes that Hubble may have glimpsed suggest that ocean material reaches the surface, ejected into space where spacecraft can sample it. The chaos terrain suggests that the ice shell is not the impermeable barrier it might appear to be, and now a spacecraft designed specifically to study this hidden ocean is travelling toward Jupiter at speeds that would carry it from New York to Los Angeles in less than 5 minutes. Within a decade, our understanding of Europa will transform from speculation to data, from hypothesis to observation, from wonder to knowledge. The instruments aboard that spacecraft represent some of the most sophisticated sensing technology humanity has ever created. The engineers who built them pushed against the limits of what is possible, creating devices capable of detecting molecules at parts per trillion concentrations, imaging features smaller than a house from thousands of kilometers away, peering through kilometers of ice to map hidden structures, measuring gravity variations caused by water sloshing in an underground ocean. Each instrument is a masterpiece of precision engineering, designed to survive the journey through deep space, designed to function in the most intense radiation environment in the solar system, designed to return data that will reshape our understanding of what is possible. The scientific teams waiting to receive that data have prepared for decades. They have built models predicting what the instruments will see under various scenarios. They have developed analysis techniques capable of extracting meaning from raw measurements. They have debated interpretations of hypothetical observations, rehearsing the controversies that will erupt when real data arrives. They have published papers establishing their frameworks, their methods, their predictions. When the Clipper finally returns its first observations, these teams will be ready to transform ones and zeros into knowledge. The transformation will not be instant. The first images will show familiar features, the same fractured ice that Voyager and Galileo observed, though in greater detail and from new angles. The first spectra will confirm known surface compositions while hinting at variations that will require months of analysis to interpret. The first radar returns will show reflections whose meaning will be debated for years. But gradually, flyby after flyby, dataset after dataset, the picture will sharpen. The integration of all these observations into a coherent understanding of Europa will require the full breadth of planetary science expertise. Geophysicists will model the interior structure consistent with gravity and magnetic field measurements. Glaciologists will interpret the radar data in light of their experience with terrestrial ice sheets. Geochemists will analyse the spectra to identify specific minerals and molecules. Astrobiologists will assess whether the observed conditions could support life as we understand it. Each specialist will contribute pieces of the puzzle, and only through collaboration will the full picture emerge. This collaborative process has already begun, even before the spacecraft has reached its destination. The science teams have been working together for years, coordinating their observation plans, their data-sharing protocols, their analysis approaches. They have run simulations of the mission operations, practicing the decisions they will need to make when real data starts flowing. They have established working groups focused on specific questions, ensuring that expertise is concentrated where it is most needed. The human infrastructure for transforming Clipper data into knowledge is as carefully designed as the spacecraft itself. The mission also embodies a commitment that extends beyond scientific curiosity. NASA does not spend $5 billion on a mission to satisfy idle wondering. The investment reflects a collective judgment that understanding Europa matters, that the question of life beyond Earth deserves the immense resources required to pursue an answer. This judgment was made by officials appointed by elected leaders, using funds appropriated by legislative bodies, in accordance with priorities established through democratic processes. The Clipper mission is, in a very real sense, a statement by human civilization about what we consider important. Other priorities competed for those resources. Other missions were proposed and rejected. Other questions were deemed less urgent, less important, less deserving of investment. The decision to build and launch the Clipper was simultaneously a decision not to pursue countless other possibilities. This is the nature of resource allocation in a world of scarcity. Every choice is also a renunciation. Yet the choice was made. The resources were committed. The spacecraft was built, tested, and launched. It now travels through space toward a destination it will reach regardless of what happens here on Earth. Changes in leadership, shifts in priorities, economic crises, pandemics, wars, none of these will prevent the Clipper from reaching Jupiter in 2030. The mission represents an irreversible commitment, a bet placed on a question that cannot be unasked. And this brings us to perhaps the deepest aspect of the Clipper mission, an aspect that has received less attention than the engineering or the science, but that may ultimately matter more. By sending this spacecraft to Europa, by designing it specifically to assess the Moon's habitability, by building instruments capable of detecting potential biosignatures, humanity has made a choice about what questions we are willing to confront. We have decided that we want to know whether we are alone, even though we do not know what that knowledge will mean. The philosophers have a term for questions that reshape everything once answered. They call them existential questions, not because they threaten existence, but because they redefine what existence means. The question of extraterrestrial life belongs to this category. It sits alongside questions about the nature of consciousness, the origin of the universe, the foundation of morality. These are questions that, once engaged, cannot be disengaged. They change the asker in the asking. For most of human history, the question of life beyond Earth remained safely in the realm of speculation. Ancient thinkers pondered whether other worlds might be inhabited, but their ponderings carried no immediate consequences. Medieval theologians debated whether God might have created life elsewhere, but the debate remained abstract, untethered to any possibility of resolution. Even the early astronomers who trained their telescopes on Mars and speculated about canals and civilizations operated in a space where the question could be entertained without risk of answer. The impossibility of knowing preserved a kind of innocence. The Clipper mission ends that innocence, not because it will necessarily find life, but because it could. The instruments aboard the spacecraft are capable of detecting signs that would be difficult to explain through purely geological processes. If those instruments return data showing complex organic molecules in specific ratios, if they detect chemical gradients consistent with metabolic activity, if they find structures that resemble cellular organization, humanity will face a moment of reckoning that cannot be postponed or ignored. Consider what it would mean to receive such data. Not definitive proof of life, perhaps, but strong evidence. Patterns that suggest, indicators that point. The scientific community would respond with appropriate caution, emphasizing the need for further investigation, warning against premature conclusions, designing follow-up missions to confirm or refute the initial findings. This is the proper response, the response that honors the scientific method and respects the magnitude of the claim. Extraordinary claims require extraordinary evidence, and the claim of extraterrestrial life is the most extraordinary claim imaginable. But science does not operate in a vacuum. The data that reaches the scientific community will also reach the public. Press releases will be issued, news organizations will report, social media will amplify. The careful qualifications that scientists attach to their statements will be stripped away in the transmission, replaced by headlines that capture attention through boldness rather than accuracy. NASA finds signs of life on Europa will trend worldwide, while the actual paper, with its hedged language and technical caveats, remains unread by all but specialists. This gap between scientific communication and public understanding creates a peculiar challenge. The scientists studying Clipper data will know exactly how uncertain their findings are. They will understand the difference between suggestive evidence and conclusive proof. They will appreciate the many alternative explanations that must be ruled out before biological origin can be claimed, but the public will not share this understanding. The public will respond to the simplified version, the version that confirms or denies in absolute terms. The psychological impact of even ambiguous findings should not be underestimated. Human beings are meaning-making creatures. We construct narratives that explain our place in the world, and those narratives shape how we think about ourselves, our responsibilities, our futures. The dominant narrative for all of recorded history has positioned humanity as either alone in the cosmos or surrounded by beings so distant and hypothetical that they might as well not exist. We have built our philosophies, our religions, our political systems, our economic structures, our art and literature, on foundations that assume Earth is the only place where life thinks and feels and wonders. Evidence of life on Europa, even microbial life, even life that might be microbial, would crack those foundations. Not shatter them, perhaps, but crack them in ways that would be felt across every domain of human thought. If simple life exists in the oceans of Europa, then simple life probably exists in countless other locations throughout the galaxy. The universe that seemed silent would suddenly seem populated. The isolation that defined our condition would become a temporary state rather than an eternal truth. Some people would welcome this shift. They would see it as confirmation of hopes they had always held, validation of intuitions they could never prove. The cosmos would feel friendlier, less empty, more like home. The loneliness of existence on a small planet orbiting an ordinary star in an unremarkable galaxy would give way to a sense of belonging, of participation in something larger than any single world could contain. Others would find the shift deeply troubling. Religious traditions that place humanity at the centre of creation would face challenges they have contemplated abstractly, but never confronted concretely. What does it mean to be made in the image of God if other beings also exist? What are our responsibilities toward life that arose independently, following its own path, serving its own purposes? These questions have answers, and theologians have been developing those answers for decades in anticipation of exactly this moment. But the answers remain untested, academic exercises that have not yet been subjected to the pressure of actual discovery. The Clipper mission brings that pressure closer. Every day the spacecraft travels toward Jupiter is a day closer to the moment when abstract questions become urgent ones. The theological frameworks that seemed adequate when extraterrestrial life was purely hypothetical will be tested against the reality of actual findings. Some frameworks will prove robust, capable of incorporating new knowledge without fundamental revision. Others will require significant reinterpretation. Still others may simply fail, unable to accommodate a universe different from the one they were designed to explain. This is not an argument against seeking knowledge. The history of science is a history of frameworks being tested and found wanting, of comfortable assumptions being overturned by stubborn facts. Copernicus displaced Earth from the centre of the solar system. Darwin displaced humanity from the pinnacle of creation. Einstein displaced absolute time and space from the foundations of physics. Each displacement caused distress, each required adjustment, each ultimately enriched human understanding more than it impoverished human confidence. The discovery of extraterrestrial life would join this sequence, another step in the long process of learning to see ourselves clearly. But the adjustment period should not be minimized. Previous displacements played out over decades or centuries, giving populations time to absorb new ideas, to integrate them into existing worldviews, to develop new frameworks that preserved what mattered while accommodating what had changed. The Clipper mission operates on a different timescale. Data will flow from Jupiter at the speed of light. Analysis will be published in peer-reviewed journals within months. Public awareness will follow within days or hours. The adjustment that previous displacements achieved over generations may need to happen in years. We do not know how humanity will respond to this accelerated timeline. We have no precedent, no historical analogue, no experience on which to draw. The discovery of the New World is sometimes cited as a comparable moment, a time when European understanding of Earth's geography expanded dramatically to include previously unknown continents and peoples. But that analogy breaks down under examination. The New World was discovered by individual explorers whose reports could be questioned, doubted, dismissed by those who found them inconvenient. The existence of the Americas took decades to be fully accepted, and even longer to be integrated into European consciousness. Clipper data will not afford that luxury. The spacecraft carries instruments whose readings can be verified, measurements whose accuracy can be confirmed, observations whose implications cannot be wished away. The irreversibility of the mission takes on new meaning in this light. The spacecraft cannot be recalled, cannot be redirected, cannot be prevented from reaching its destination and conducting its observations. The data it gathers will be transmitted back to Earth and will become part of the permanent record of human knowledge. Whatever that data shows, whatever it implies, whatever questions it raises or answers, will be available to anyone who chooses to engage with it. The question that humanity has sent the Clipper to investigate is a question that will receive an answer. The only uncertainty is what that answer will be. This commitment deserves contemplation. In ordinary life, we preserve the option to look away. When confronted with uncomfortable truths, we can choose denial, distraction, reinterpretation. We can construct narratives that protect us from knowledge we prefer not to possess. The mechanisms of self-deception are well documented by psychologists, and they serve important functions. They allow us to maintain functional lives in the face of realities that might otherwise overwhelm us. They permit action in a world too complex and threatening to be faced with complete honesty. The Clipper mission bypasses these mechanisms. It creates knowledge that cannot be unknown, evidence that cannot be unseen, findings that cannot be unfound. By the time the spacecraft completes its mission, humanity will possess observations whose implications will be debated but whose existence will be undeniable. We are choosing to know, choosing to confront, choosing to face whatever answers the universe holds. This choice reflects something important about the species that made it. Among all the possible uses of our intelligence, our resources, our technological capabilities, we have elected to pursue a question whose answer may disturb us. We have invested billions of dollars not in comfort or security, but in knowledge that may require us to revise fundamental assumptions about our place in the cosmos. We have built a spacecraft and launched it toward a frozen moon because we would rather know than wonder. Some would call this courage. Others might call it recklessness. The appropriate label depends on judgments about risk and reward that cannot be made objectively. What is undeniable is that the choice has been made. The spacecraft is en route. The question is being asked. The answer is approaching. The scientific teams preparing for Clipper's arrival understand this weight. They do not discuss it often, not because they are unaware, but because it serves no practical purpose. Their job is to prepare for data, to develop analysis tools, to establish protocols for interpreting observations. The philosophical implications of their work are not irrelevant, but they are secondary to the technical demands of the moment. There will be time for philosophy later. Right now there are algorithms to test, calibration procedures to refine, observation sequences to plan. Yet even in the midst of technical work, the larger significance intrudes. A graduate student designing a pattern recognition algorithm for ice radar data pauses to consider what patterns might mean. A postdoctoral researcher calibrating a mass spectrometer against known compounds contemplates what unknown compounds might indicate. A senior scientist reviewing mission timelines thinks about how the timeline of their career has led to this moment, this mission, this question. The work is technical, but the context is existential. The mission also forces consideration of what constitutes evidence. What would we need to see in Clipper data to believe that life exists on Europa? The question is not as simple as it might seem. Direct observation of living organisms is not possible with Clipper's instruments. The spacecraft will not return images of swimming creatures or growing colonies. Any evidence for life will be indirect, inferential, dependent on reasoning from observations to conclusions. Chemical signatures offer one type of evidence. Living systems produce characteristic molecules, consume characteristic reactants, generate characteristic waste products. Terrestrial life has left chemical fingerprints throughout Earth's environment, patterns that would be difficult to explain through purely abiotic processes. If similar patterns were detected in Europa's ocean material, they would constitute suggestive evidence, but suggestive is not conclusive. Chemistry can produce surprising results even without biology. Minerals can catalyze reactions, radiation can transform molecules, heat and pressure can create complexity. Every chemical signature that might indicate life has alternative explanations that must be ruled out before biological origin can be claimed. Structural evidence offers another type. Living things create organized structures, cells and membranes, and compartments that maintain internal environments distinct from external conditions. If Clipper's instruments detected microscopic structures with characteristics consistent with cellular organization, that detection would carry significant weight. But structures can arise from non-biological processes as well. Crystals organize themselves through purely physical principles. Vesicles form spontaneously when certain molecules encounter water. The mere existence of structure does not prove the existence of life. The specific characteristics of the structure matter, and those characteristics may be ambiguous, subject to interpretation, consistent with multiple explanations. The challenge is compounded by the nature of a remote observation. Clipper will not land on Europa. It will not drill through the ice or sample the ocean directly. It will observe from orbit, using instruments that can detect what passes through space or reflects from surfaces. The ocean lies kilometers below the ice, protected from direct observation by frozen barriers that no remote sensor can fully penetrate. Whatever evidence Clipper gathers will be evidence of what reaches the surface or affects observations from above. The ocean's secrets will remain secrets unless they find expression in ways that Clipper's instruments can detect. This limitation focuses attention on Europa's cracks and plumes, the chaos terrain where ice blocks have shifted and rotated, the lineae that scar the surface in patterns suggesting recent activity, the possible plumes that may occasionally vent material from below. These features represent windows into the interior, places where ocean material may reach the surface where instruments can analyze it. Clipper's observation plan concentrates attention on these features precisely because they offer the best hope of detecting what lies beneath. If the spacecraft flies through an active plume, its mass spectrometers will sample whatever molecules that plume contains. If it observes fresh material deposited along crack margins, its spectrometers will identify whatever compounds that material comprises. If it detects thermal anomalies suggesting recent upwelling, its radar will map whatever structures underlie those anomalies. Each observation provides a data point. Each data point constrains possibilities. The accumulation of data points over dozens of flybys will build a picture that no single observation could create. The picture may be ambiguous. This is the most likely outcome, the outcome for which the science teams are most thoroughly prepared. The data will suggest, will indicate, will be consistent with or inconsistent with, but will probably not prove. The mission may end not with a definitive answer, but with a more refined question, a clearer understanding of what would need to be observed to reach certainty. This outcome would not represent failure. It would represent progress of the kind that science typically achieves, incremental rather than revolutionary, narrowing possibilities rather than eliminating them. But the mission might also produce data that shifts the balance of probabilities so dramatically that reasonable doubt becomes unreasonable. This outcome is unlikely, but it is not impossible. If Clipper's instruments detected multiple independent lines of evidence all pointing toward biological activity, if chemical signatures and structural features and energy gradients all aligned in ways that abiotic processes cannot explain, the scientific community would face a moment of decision. At some point, continued skepticism becomes stubbornness. At some point, the most parsimonious explanation is the extraordinary one. The threshold for that shift is not defined in advance. Scientific consensus emerges through debate, through challenge, through the accumulation of evidence that eventually overwhelms resistance. The exact point at which the community would conclude that Europa harbours life cannot be specified ahead of time. Different scientists will reach that conclusion at different points. Some will hold out for direct observation even after indirect evidence has convinced most of their colleagues. Others will embrace the conclusion quickly, perhaps too quickly, based on evidence that later proves less compelling than initially thought. The process will be messy, contentious, human, and this process will play out in public view. Unlike many scientific debates that unfold within specialised journals read only by experts, the debate over evidence for European life will attract global attention. Every new paper will be reported, every conference presentation will be tweeted, every disagreement among scientists will be amplified and distorted by media outlets seeking engagement over accuracy. The scientific process, designed for careful deliberation and gradual consensus building, will be subjected to pressures it was never designed to withstand. This observation is not a criticism of media or public interest. The public has every right to know what their investment in the Clipper mission has revealed. The media performs an essential function in making scientific findings accessible to non-specialists. The pressures are inevitable consequences of pursuing a question that matters beyond the narrow confines of scientific research. The observation is simply that the conditions under which the Clipper findings will be evaluated are different from the conditions under which most scientific findings are evaluated. The stakes are higher. The attention is greater. The room for measured deliberation is smaller. The scientists know this. They have watched previous discoveries become distorted in transmission, watched careful qualifications get stripped away, watched nuanced findings get reduced to binary headlines. They have learned from these experiences, developing communication strategies that anticipate misunderstanding and build in redundant clarifications. They prepare press releases with exceptional care, knowing that phrases will be quoted out of context and images will be reproduced without captions. They train for press conferences, practicing how to convey complexity without losing accuracy, how to express appropriate uncertainty without seeming evasive. These preparations help, but they cannot fully bridge the gap between scientific discourse and public understanding. That gap exists because science and media operate according to different logics. Science rewards caution, qualification, acknowledgement of uncertainty. Media rewards confidence, clarity, novelty. Science values being right over being first. Media values being first over being right. Science builds knowledge incrementally, each finding building on previous findings and awaiting confirmation from subsequent findings. Media treats each finding as an isolated event, a story with beginning, middle, and end. When Clipper's findings begin to flow, these different logics will collide. Scientists will describe possibilities and probabilities, and reporters will translate those descriptions into certainties and doubts. Scientists will emphasize what remains unknown, and headlines will proclaim what has been discovered. Scientists will request patience while analysis proceeds, and audiences will demand immediate conclusions. The collision is unavoidable. The question is only how much damage it causes. The damage may be minimal. Public audiences are more sophisticated than they are sometimes credited. Many people understand that initial reports are often corrected, that headlines simplify, that science proceeds through revision rather than revelation. The backlash against sensationalized science reporting has grown in recent years, with audiences developing healthy skepticism toward extraordinary claims. The public may prove capable of holding uncertainty, of waiting for consensus, of resisting premature conclusions, or the damage may be significant. Misinformation spreads faster than correction. First impressions prove durable even when shown to be incorrect. People believe what they want to believe, fitting new information into existing worldviews, rather than revising those worldviews to accommodate new information. The discovery of potential signs of life on Europa could become entangled with existing controversies, appropriated by factions seeking validation for unrelated agendas, distorted beyond recognition by the time it reaches many audiences. Both outcomes are possible, neither is certain. The mission team can control what they communicate, but not how that communication is received. They can prepare for public engagement, but not determine how engagement unfolds. They can offer accurate information, but not ensure that accuracy survives transmission. Their responsibility ends at the boundary between their expertise and the broader public sphere. Beyond that boundary, the findings will take on lives of their own. This loss of control may be the most profound aspect of the Clipper mission's irreversibility. Not the physical trajectory of the spacecraft, which is merely a matter of orbital mechanics. Not the inevitability of data collection, which is merely a consequence of functioning instruments, but the release of knowledge into a world that will interpret that knowledge in ways its discoverers cannot predict or control. Once the findings are published, they belong to humanity, to be used and misused, understood and misunderstood, celebrated and feared. The scientists who devoted their careers to this mission will have no more authority over its meaning than anyone else. This may be as it should be. Scientific discoveries have never belonged solely to their discoverers. The double helix belonged to Watson and Crick only briefly before belonging to everyone. General relativity belonged to Einstein only momentarily before becoming the common inheritance of all who sought to understand space and time. The structure of the atom, the age of the universe, the mechanism of evolution, all passed quickly from the possession of their discoverers into the shared property of human knowledge. The discoveries that Clipper may enable will follow the same path, but the path is steeper this time. The discovery of life beyond Earth, if it comes, will not be a discovery that changes how experts think while leaving ordinary life largely undisturbed. It will be a discovery that reaches into every domain, that raises questions in contexts far removed from science, that demands response from institutions and individuals who never asked to be involved. The mission team knows this. They have accepted the responsibility it entails. They proceed anyway. The question they carry with them across 500 million miles is not merely scientific. It is existential in the most literal sense of that overused word. Does existence extend beyond our world? Have the conditions that produced consciousness here produced it elsewhere? Are we alone, or have we always been accompanied by neighbours we simply lacked the means to detect? These questions have haunted human imagination since the first ancient stargazer wondered whether the points of light overhead might harbour beings looking back. Now, for the first time in human history, we possess the technology to move from wondering to knowing. The Clipper mission represents not just an engineering achievement, but a philosophical threshold. We have built the instrument that could answer the oldest question. We have launched it toward the most promising target. We have committed ourselves to receiving whatever answer the universe provides. The spacecraft hurtling through darkness at this moment is a question mark made physical, a 12,000-pound expression of humanity's refusal to remain ignorant of its cosmic context. What makes this moment different from all previous moments of discovery is its finality in one specific dimension. Previous discoveries about life's possibilities could always be revised, qualified, complicated by subsequent findings. The discovery that extremophiles could survive conditions once thought lethal expanded our conception of habitability, but left the fundamental question open. The discovery of organic molecules on Mars and in interstellar space suggested that chemistry trends toward complexity throughout the universe, but proved nothing about biology specifically. The detection of thousands of exoplanets, many inhabitable zones, vastly increased the number of potential abodes for life, but provided no evidence that any of them actually hosted life. Each discovery moved the conversation forward while leaving the core uncertainty intact. Clipper's potential findings would be categorically different. If the spacecraft detects biosignatures in Europa's ocean material, we will know that life exists beyond Earth. Not suspect, not hypothesize, not consider likely, but know with the certainty that comes from direct detection. The knowledge would be irreversible in a way that no previous finding has been. You cannot unknow the existence of extraterrestrial life any more than you can unknow that Earth orbits the Sun rather than vice versa. The discovery would become a permanent feature of human understanding, a fact as settled as any fact science has established. The mission team has contemplated this permanence throughout the long years of development. In engineering meetings focused on thermal management and radiation shielding, in science planning sessions devoted to observation sequences and data prioritization, in management reviews tracking budget and schedule, the ultimate purpose of the mission has remained present like a silent observer. They are building a machine designed to change everything. The mundane details of spacecraft construction connect to the most profound questions humanity has ever asked. The engineer calculating thermal loads on the radiation vault is contributing to answering whether we are alone. The scientist calibrating the mass spectrometer is preparing to detect evidence of cosmic neighbours. The project manager tracking milestones and deliverables is shepherding a mission that could redefine humanity's understanding of existence itself. The disconnect between the ordinary nature of the work and the extraordinary nature of its purpose has been a constant companion throughout the development process. How do you maintain focus on technical details when those details serve such overwhelming ends? How do you treat problems as solvable when the success you're working toward could be civilization-altering. The team has managed this tension through compartmentalization, through focusing on immediate challenges while trusting that the larger purpose will take care of itself. But the larger purpose never quite recedes from awareness. It waits in the background of every discussion, the silent justification for every effort, the reason why people have devoted their careers to a single mission. Now the development is complete. The spacecraft is en route. The years of preparation have given way to the years of waiting. The mission team must occupy a strange temporal space, past the completion of their primary task but before the completion of their ultimate purpose. The spacecraft they built is functioning perfectly, its systems healthy, its trajectory precise. But the data they await will not arrive for years. They must maintain the patience that science demands while feeling the impatience that their purpose inspires. They must attend to the ongoing tasks of mission operations while knowing that the truly significant work will not begin until Europa approaches. They must sustain their commitment through the long, quiet middle of the journey, when the spacecraft is too far from launch to feel new and too far from arrival to feel imminent. This waiting is its own form of irreversibility. Time passes in one direction only. Each day brings the spacecraft closer to its destination, while bringing the team members closer to the conclusions of their careers. Some team members who began working on Clipper in its earliest conceptual phases will not live to see its arrival. Others will be retired, watching from a distance as colleagues they trained receive the data they spent decades preparing to collect. The mission spans a significant portion of human life, long enough that the people who began it and the people who complete it may substantially differ. The continuity of the mission must be maintained through institutional structures rather than individual presence. Knowledge must be transferred, skills must be taught, purposes must be communicated across generations of team members. The spacecraft carries not just instruments, but the accumulated commitment of everyone who contributed to its creation, including many who will never see its findings. The loneliness of the waiting mirrors, the loneliness of the spacecraft itself. Europa Clipper travels through emptiness so profound that human minds struggle to comprehend it. In the vast spaces between planets, matter is scarce almost beyond imagining. A few atoms per cubic centimetre, stray hydrogen and helium, the occasional dust grain left over from the solar system's formation, and nothing else. The spacecraft moves through this vacuum like a message in a bottle thrown into an ocean of nothingness. Light takes minutes to travel from the spacecraft to Earth, then more minutes for responses to travel back. The loneliness is not merely metaphorical but physical, measured in the time required for communication, in the impossibility of real-time interaction, in the autonomy the spacecraft must exercise when unexpected situations arise. The onboard computer must make decisions without consulting Earth when events unfold too quickly for the light speed delay to permit consultation. The spacecraft must be intelligent enough to keep itself alive through circumstances its creators could not anticipate. It carries some portion of human judgment frozen into code, decision trees that embody the wisdom of engineers and scientists, who will be far away when that wisdom is needed. This autonomy raises questions that the mission team has contemplated carefully. What if the spacecraft discovers something that demands immediate response? Some findings so significant that waiting for instructions from Earth would be intolerable. What if the instruments detect unambiguous evidence of biological activity during one of the early flybys, years before the mission's planned conclusion? The spacecraft cannot call a press conference. It cannot consult with ethicists or theologians or political leaders. It can only record what it observes and transmit that recording to Earth at the speed of light, arriving some 40 minutes after the observation itself. The humans on Earth would learn of the discovery with a time delay that, while brief by cosmic standards, would feel interminable by human standards. 40 minutes of knowing that the data was in transit. 40 minutes of waiting for the most significant message ever received. 40 minutes that would become legendary in their excruciating anticipation, analysed and dramatised and remembered for as long as humanity endures. The data would arrive as a stream of ones and zeros, indistinguishable at first from any other transmission. Engineers would process the telemetry, extracting science data from housekeeping data, routing information to appropriate teams for analysis. The biosignature detection, if it occurred, would emerge from this routine processing, initially just another data product awaiting interpretation. Someone would look at a spectrum or a mass analysis or an imaging result and recognize what they were seeing. Someone would realize that the pattern before them was not mineral, not geological, not chemical in any abiotic sense. Someone would understand, in a moment that would divide their life into before and after, that they were looking at evidence of life that had evolved independently of Earth. The recognition might come quietly, a growing certainty rather than a sudden revelation. Or it might come as a shock, an immediate unmistakable signal that permitted no doubt. Either way, the person experiencing that recognition would carry it alone for at least a few seconds, holding knowledge that would soon belong to everyone but that briefly belonged only to them. Those seconds would be the last moment of the old world, the final instant before everything changed. The protocols for such a discovery have been developed and refined over decades. NASA and the broader astrobiology community have established procedures for validating and announcing detections of extraterrestrial life, designed to ensure that claims are supported by evidence and that announcements are handled responsibly. The Clipper team would not rush to press conferences or leak to media contacts. They would follow the protocols, checking and rechecking, consulting with colleagues, waiting for confirmation before claiming detection. The process would take time, perhaps weeks or months, a period of agonizing secrecy while analysis proceeded and confidence grew. During this period, a growing circle of people would know or strongly suspect what had been found, while the wider world remained unaware. The knowledge would spread through the scientific community like ripples from a stone dropped in still water, each new person informed becoming another keeper of the secret. The burden of that secret would be considerable. The temptation to share it would be immense. The protocols would be tested against the most compelling revelation in human history. Eventually the announcement would come. The specifics would depend on circumstances that cannot be predicted, but certain elements would be constant. There would be a press conference carefully prepared, with visuals and explanations designed for general audiences. There would be a scientific paper or papers submitted to peer review and publication in major journals. There would be statements from NASA leadership, from government officials, from international partners and scientific organizations. The announcement would be coordinated but not controlled, rehearsed but not scripted for every contingency. And then the secret would be a secret no longer. The knowledge would belong to everyone. The aftermath of that announcement is where prediction fails most completely. We can model the spacecraft's trajectory with extraordinary precision. We can calculate the radiation doses its instruments will receive. We can estimate the likelihood of detecting various biosignatures given various assumptions about Europa's habitability. But we cannot model the human response to discovering that we are not alone. We cannot calculate how societies will react, how institutions will adapt, how individuals will integrate this knowledge into their lives. We cannot estimate the likelihood of various social outcomes given various assumptions about human nature. The prediction fails because the event has no precedent. Nothing in human experience provides a template for understanding how we would respond to confirmed extraterrestrial life. Even microbial life. Even life limited to a single distant moon. The analogies all break down under scrutiny. The discovery of the Americas, often invoked as a comparison, involved contact between human societies that, however different, were recognizably human. The Copernican revolution, another common comparison, changed how we understood our cosmic position but revealed no new inhabitants of the cosmos. The discovery of deep-sea hydrothermal vents, perhaps the closest analogy in terms of life's unexpectedness, occurred in settings remote from most human experience and involved organisms that, however strange, were clearly earthly in their chemistry and origins. None of these precedents capture what it would mean to find life that shares no history with life on Earth, life that represents an independent experiment in the transition from chemistry to biology. The philosophical implications would unfold over years and decades, rippling through theology and ethics and law and countless other domains. But the initial response would likely be emotional rather than philosophical, a feeling rather than a thought. Wonder, perhaps. Fear, perhaps. Joy or dread or some complex mixture that defies simple naming. The response would vary enormously across individuals and cultures, shaped by expectations and beliefs and temperaments that differ as widely as humanity itself differs. Some would celebrate the discovery as validation of their conviction that life pervades the cosmos. Others would deny the discovery. fitting it into conspiratorial frameworks that reject unwelcome revelations. Most would fall somewhere between these extremes, accepting the discovery but struggling to integrate it into worldviews that had never quite prepared for such integration. The Europa Clipper mission team has no control over these responses. Their responsibility ends at the accurate collection and reporting of data. What happens after reporting is beyond their authority and largely beyond their capacity to influence. They can communicate clearly, correct misconceptions, provide context and interpretation, but they cannot determine how their findings are received any more than a letter writer can determine how a letter is read. The meaning of the mission will be made by humanity as a whole, not by the mission team specifically. This relinquishment of control is perhaps the final irreversibility of the mission, the ultimate commitment it entails. The team has spent decades preparing to ask a question. Soon they will have to live with whatever answer they receive, knowing that the answer belongs not to them, but to the species whose question they carried. The trajectory continues. The spacecraft crosses millions of additional miles with each passing month. The Sun growing slowly smaller in its rear sensors, Jupiter growing slowly larger ahead. The instruments sleep their programmed sleep, conserving power, awaiting activation. The radiation vault shields its precious electronics, preparing for the harsh environment to come. The propellant tanks hold their reserves, ready for the maneuvers that will thread the spacecraft through Jupiter's gravitational maze. Everything that can be prepared has been prepared. Everything that could be controlled has been controlled. What remains is the mission itself, the flybys and observations and data collection that will determine whether the preparation was sufficient, whether the controls were adequate, whether the question humanity asked can be answered. The ice awaits. 10 to 15 miles thick in most regions, perhaps thinner in others, it covers Europa's ocean like a lid on a vast pressure cooker. The tidal flexing that keeps the ocean liquid also flexes the ice, creating the patterns of ridges and cracks that Voyager first photographed decades ago. Somewhere beneath that ice, the ocean circulates in patterns we cannot yet see, driven by temperature gradients and the slow release of heat from the rocky seafloor. Somewhere in that circulation, chemistry progresses through reactions we cannot yet measure, and somewhere in that chemistry, molecules arrange themselves in patterns we cannot yet interpret. Patterns that may or may not include the patterns we call life. The spacecraft will not penetrate the ice. It will not descend into the ocean. It will not touch the seafloor where the chemistry is richest. It will fly overhead at 25,000 miles per hour, sampling what the ice releases, imaging what the surface reveals, measuring what the instruments can detect through the limitations of distance and velocity. The data will be incomplete, suggestive rather than conclusive in many respects. The scientist will struggle to distinguish signal from noise, pattern from randomness, biology from geology. The analysis will take years even after the data is collected, with interpretations shifting as new evidence accumulates. The answer, when it comes, may be frustratingly provisional, a probability rather than a certainty, a likelihood rather than a proof. Or the answer may be unambiguous, a detection so clear that doubt becomes unreasonable. The mission team cannot know which outcome awaits them. They can only ensure that their instruments are capable of detecting what is there to be detected, that their analysis methods are rigorous enough to interpret what is detected, that their communication is clear enough to convey what is interpreted. The rest is up to Europa. In this sense, the mission is an act of trust in the universe. The team has done everything within human power to ask the question effectively. Now they must trust that the universe will provide an interpretable answer. They must trust that Europa's ocean, if it harbours life, will reveal that life through signs accessible to their instruments. They must trust that the chemistry of alien biology, if such biology exists, will be different enough from abiotic chemistry to be recognisable. They must trust that the patterns of life, whatever form they take, will be patterns that human minds can perceive and human instruments can measure. These are not guarantees but hopes, not certainties but reasonable expectations based on our understanding of biology and chemistry. The universe is not obligated to make its secrets accessible. It is not required to reveal itself in ways we can understand, but we proceed as if it will, as if the questions we ask will receive answers we can interpret. This trust is fundamental to science itself, the faith that underlies all empirical inquiry. The universe is comprehensible, its patterns can be discerned, its truths can be uncovered through patient observation and careful analysis. The Clipper mission embodies this faith as concretely as any scientific endeavour has ever embodied it. The ice moon orbits Jupiter once every 3.5 Earth days, its tidally locked face forever turned toward its massive parent. The flexing is constant, the heating is continuous, the ocean is maintained against all the cold of outer space by the gravitational embrace of a world more massive than all other planets combined. This system has operated for billions of years. If life emerged in Europa's ocean, it has had time enough to diversify into ecosystems of staggering complexity. If life did not emerge, the conditions that could have allowed emergence have persisted nonetheless. A laboratory of prebiotic chemistry operating at scales and timescales that dwarf any experiment humans could conduct. Either outcome is scientifically significant. Either outcome transforms our understanding of life's prevalence and specificity. The mission succeeds if it provides data sufficient to distinguish between these outcomes, regardless of which outcome the data supports. But let us not pretend that the outcomes are equally thrilling. The discovery of life would echo across centuries. The confirmation of sterility, while informative, would not carry the same weight. The mission team hopes for the more dramatic outcome even as they prepare for the more mundane one. They are human beings, not dispassionate automata. They would prefer to discover neighbours rather than confirm solitude. They would prefer to transform human understanding rather than merely refine it. This hope is not a bias that distorts their science, but a motivation that energizes their commitment. They work with extraordinary dedication because the possible payoff is extraordinary. The professionalism that ensures objectivity in analysis coexists with the passion that drives the analysis forward. Now the waiting deepens into its longest stretch. The cruise phase will consume years, the spacecraft falling ever deeper into the sun's gravity, well before climbing back out toward Jupiter's embrace. The team will monitor, will adjust, will maintain vigilance through the long quiet. They will age, will change, will carry the mission with them through whatever else their lives contain. Some will drift away to other projects, their contributions complete. Others will remain, their commitment unbroken, their attention fixed on the day when the waiting ends and the flybys begin. The mission will persist through changes of administration and shifts of priority, through budget cycles and policy debates, through all the institutional turbulence that affects large, long-duration projects. It will persist because it must, because the spacecraft is already flying, because the question has already been asked and cannot be withdrawn. Europa waits, indifferent to our anticipation. Its ice stretches across hundreds of millions of square miles, cracked and refrozen and cracked again in patterns that record billions of years of tidal stress. Its ocean circulates in darkness, untouched by sunlight, unmeasured by instruments, unknown in its particulars though inferred in its existence. Its secrets keep themselves, neither hidden nor revealed, simply present, waiting for the means of discovery to arrive. The spacecraft closes the distance, 1 mile at a time, 1 second at a time, carrying humanity's most audacious instrument toward humanity's most profound question. It carries the work of thousands of engineers and scientists and technicians and managers and contractors and administrators and countless others who contributed in ways large and small to its construction and launch. It carries the hopes of a species that has always wondered whether it is alone, and that now, for the first time, possesses the means to find out. It carries the burden of a question that may not have a comfortable answer, and the promise of a question that may finally receive any answer at all. The mission began in imagination, in the minds of scientists who looked at Voyager images and recognized the significance of Europa's cracked ice. It progressed through proposal and advocacy, through funding battles and technical challenges, through the long, slow accumulation of resources required to translate vision into hardware. It survived near cancellation, was resurrected, was scaled and descoped and redesigned until it achieved the form now hurtling through space. It was built, tested, transported, integrated, tested again, loaded with propellant, mated with its rocket, launched into the Florida sky, separated, deployed, activated, and dispatched on its journey. Each phase was irreversible. Each commitment led to subsequent commitments. Each decision closed off alternatives and opened new necessities. The mission team made thousands of choices, each small in itself, that together created the trajectory now unfolding. That trajectory leads to Jupiter's radiation environment, to the orbital dance that will protect the spacecraft while enabling its observations, to the flybys that will carry instruments through plumes if plumes are active, to the data that will travel back to Earth at the speed of light, to the analysis that will occupy scientists for years or decades, to the conclusions that will enter human understanding and remain there forever. The trajectory leads, ultimately, to an answer. We do not know what the answer will be. We know only that we have committed ourselves to receiving it, that we have launched the instrument that will provide it, that we have foreclosed the option of remaining ignorant. The question has been asked. The answer will come. Perhaps it will come as a detection, as unambiguous evidence of biology beyond Earth, as the most significant scientific discovery in human history. Perhaps it will come as a non-detection, as the absence of biosignatures despite thorough searching, as a constraint on life's prevalence that informs future exploration. Perhaps it will come as ambiguity, as data that suggests but does not confirm, as a mystery deepened rather than resolved. Whatever form the answer takes, it will belong to us all. The spacecraft that asked the question did so on behalf of humanity. The answer it receives will be humanity's answer. The knowledge it generates will be humanity's knowledge, to be used and interpreted and lived with for as long as humans endure. We are alone in our knowing, or we are not alone. Within a decade, we will know which. The ice moon orbits Jupiter, as it has for billions of years. The ocean circulates in darkness, as it has since before life emerged on Earth. And somewhere in the space between worlds, a spacecraft built by human hands carries human questions toward whatever answers await. The universe does not promise comfortable truths. It does not guarantee that its revelations will be welcome. It offers only the chance to understand, the opportunity to know, the privilege of replacing ignorance with knowledge, however that knowledge transforms us. We have taken that chance. We have launched the mission. We have crossed the threshold from wondering to seeking. The rest is trajectory, is time, is the patient unfolding of a journey we chose to undertake. When Europa Clipper arrives at its destination and begins its observations, it will complete a commitment made long ago. A commitment to ask the question and accept the answer. A commitment to face whatever truth the ice moon reveals about our place in the cosmos. The stars are not impossibly distant. They merely wait for us to develop the will to reach them. And Europa, far closer than any star, waits now for the spacecraft we have sent, indifferent to our hopes, unaware of our questions, holding its secrets in an ocean we have never seen but can no longer pretend does not exist. The ice is real. The ocean is real. The possibility of life is real. And soon, very soon, by the standards of cosmic time, we will know whether the life is real as well. Whatever we discover together. Whatever we learn as a species. Whatever changes for all of us. This is what it means to ask the oldest question with the newest tools. This is what it means to commit ourselves to knowledge we cannot unknow. This is what it means to be human at this moment in history, poised between ignorance and understanding, waiting for an answer we have finally found the courage to seek. The spacecraft flies on. The ice awaits. The question hangs in the void between worlds, travelling at miles per second toward its resolution. And humanity, the species that asked the question, waits on a small rocky planet orbiting an ordinary star, watching the sky, wondering what answer the darkness will return.